He said this is darker, right? Yeah, just lift it up. Otherwise, you can use other. Yeah,
Yeah, no, it may not be a bad idea to shine it from the top too. I don't know. How does it plug in?
Yeah. This is good.
Oh, it looks good.
Yeah, I don't know. You can look from your computer.
Okay.
I don't know.
Oh, this is good.
This is good, right?
Yeah,
Very good. This is very good. This is.
But that doesn't bother you, that light?
Which one?
This one?
No,
here?
no.
Okay.
That should be okay. Okay. Now I can go here. Okay. Instrument notice protection.
So
Yeah,
are you going to show you're not going to internet at all here, right? In the presentation? Good.
It's already connected to internet.
No, but you're not in the presentation. You don't show any. Okay, good.
Because what I did, I put the link and then put the Excel spreadsheet here only.
Yeah, good.
So it just goes there.
So with that, Pratap, you have, my challenge was to go between, I was not showing any internet also, to be talking without the slides and then talking with slides.
Okay.
So you have to go back and forth, right? Sometimes when you're not showing the slides, you want to be yourself on the screen fully, right? Is that Pratap? I mean, Jaram,
doesn't matter. In the corner, my thing is there, like what we did.
Okay. That way you won't be switching. You'll always be showing the slides, sharing the slides, right?
Yeah. Yeah. That should be good enough.
No, that's fine.
Then you can have a share here. That's how you do it, right?
Yeah. And there's no audio sharing in this, right? Or do you have anything playing in this presentation?
Nothing.
So you can go to presentation.
No, I was wondering where that comes.
I think you should have the, perhaps bigger portion of you show up. Maybe if you could tilt it a little more, your computer.
This way?
Perhaps.
Yeah, whatever.
Yeah,
this
now
way.
you show it better. Yeah, this way. Yeah, but it'll be difficult to write in that mode, is it? Because you have to write on the screen.
In case if somebody asks, right now, I don't have.
I
have this.
Maybe you can hold it with one hand and write it with the other.
Yeah.
Hold the screen.
Yeah, what we can do is we can cut the video off at that time and then just write it.
Yeah.
I can take it and then.
Sure. Okay. So
I put those.
Meeting has started?
Yeah, it's already 12:50.
Very good. Yeah, popular for that. Will be more. If they have any smiles.
Hi everyone, it's Juan Rojas.
I can hear somebody there.
Yeah, you should mute them. See, that's another challenge.
Yeah, that's how it happens. So you can go to stop share. And then participants. You click on mute all. There.
Oh, this one.
Yeah. And then click this, uncheck this. And then yes.
So you should only accept questions through chat box, and otherwise it will get very chaotic.
Okay. So now they can listen to hear me. Yeah.
Yeah, you are like, we just muted them.
Good morning, everyone. I hope you can hear me. If you can't, then please send a message, text a message, and then we'll look at it. Welcome to this Power System Protection course. This course was designed for a 3-credit course at University of Minnesota, and we taught for 5 years. I taught with Mark Gutzman of Excel Energy, and and later on, 22 modules were developed for as a part of CUSP, and then this was distributed. And then in 3 days, where we are meeting here, we will be covering all the protection aspects and all these modules, the topics covered in these modules in the 3 days. You should know that this was a semester-long course, and we are trying to cram it in 3 days. So we will have, I will cover 8 modules today, which looks at the basic terms that are used in power system protection. And then we look at the instrument transformers which feed information to these relays, and also mathematical tools that are you should be aware of as a protection engineer to to find out the voltages and currents if there is an abnormal event like a short circuit or an open circuit. So these are basic things which would be covered. As I mentioned to you, this is covered in 6 months, and we are trying to do it in 3 days. So please do go back and look at the modules. These were recorded 6 years back, and most of these are up to date technically, but some of the references have changed because companies have been acquired, or the IEEE documents have been updated. So we will go through everything, and if you have any questions, please do send your note, any chat, text me, and then we will try to address it. So we will start with the very first we will share this first. Okay. Okay, you should be seeing my screen, the very first slide of this presentation, Power System Protection Lectures by Pratap Mysore. When you look at my videos that were recorded 6 years back, it says that I am from HDR. I used to work there. Now I'm an independent consultant, and then I can be reached at pratap.mysore@ieee.org. Again, it is pratap.mysore@ieee.org. And this session, we will cover fundamentals of protection. The reference materials which we had given were, to a couple of books which are available free, and then they were written especially for power system practicing engineers. And also this would be a good introduction to all the students who are getting into power system protection. The first one is C.R. Mason. Mason was a design engineer who designed a lot of electromechanical relays for General Electric, and he wrote a book, Art and Science of Protective Relaying, that gives the basic concepts of the terms and also basic protection schemes. But this is a dated book, so it is good to look at it from to understand the basic concepts. And the next one is Protection and Automation Application Guide. This was formerly known as Network Protection and Automation Guide, NPAG, from Alstom. And formerly, this was from GEC Measurements. That name got changed by Alstom as NPAG, and now GE acquired Alstom, and now it is called Protection and Automation Application Guide. So if you, in the slides, if you see NPAG, it is nothing but, it's the same book, but it is the name has been changed to PAG. And now the web links which were free before are now monitored. So you have to first register a GE web page and then download. I think the links are on the web page on the CUSP site. There are also excellent books in IEEE explore.org. These are reference books, especially from Paul Anderson. There are two books. One is the fault calculation, fault analysis, and the second one is power system protection. These are excellent books for practicing engineers. They can refer to them and then use that. And IEEE guides is another way to understand a lot of these protection schemes. They cover what has been in practice in the last 5 years. And then if you go to manufacturers' documents or publications, they will provide you the latest technologies that is in this field. So essentially, we started with C.R. Mason, then you have Protection and Automation Guide, then IEEE reference books, then IEEE guides, and then also, if you look at the manufacturer's website, you understand more. And then class notes is just a reference material for you to understand the concepts, and then that could be used. We also have a CT saturation calculator, an Excel spreadsheet from Power System Relaying and Control Committee website. This is useful in understanding how CT saturates. And then if you have any problems in coordination for those practicing engineers, you can go back and see whether the CT saturated and then the relay actually saw less current than what it was supposed to see. It's a good link, and that is very helpful for you to analyze events. Now, if you look at it, I have got a 3-bus system here. We have generation, and then we step up the generated voltage to a higher level to transmit power from the generation site to the load center, where we step it down and to various levels before it comes to our homes or industries or wherever the load electricity is consumed. We also have a couple of devices, shunt reactor or shunt capacitors. The purpose of these is to maintain the voltage of the system within a specified range. So the major power components we are talking about are generators, transformers, transmission lines, switching devices, and loads. When you look at the generators, I will start with the rotating machinery. They were converting mechanical energy to electrical energy. Inputs to generate mechanical energy, they used fossil fuels to generate steam, or nuclear material is also used to generate steam. Then you have garbage burning plants. There are various other types which have a low heat content, but they are also used in generating steam that will rotate the generator. You have water, they are called hydro machines. Then we have wind machines. Then we also have tidal and geothermal. And now we have non-rotation, non-conventional generation, that is solar, and from solar energy to electricity, that is PV cells. And then we also have fuel cells, which uses chemical reaction. If you look at the generator ratings, the voltages at which they generate power is dependent on the rating of the generator, and they can go up to 26 kV. Generators, if you look at steam generators, they are the one which is installed right now is 1440 MVA. They're running at 3600 or 1800 RPM, depending on where they are used. The latest one that is in construction is 1770 megawatts. This is being built in GE, France, which was Alstom before, and this is getting shipped to United Kingdom, where they are building the first nuclear plant. There will be 2 units of this that will be sent by 2025, I think. That is what their targeted commissioning date is. Then hydro machines, we have the largest one is 700 MVA. This was first used at Itaipu in South America, border between 2 countries, where half of them generated at 50 hertz, and the next other half is generating at 60 hertz. And then the latest one is a few years back, 3 Gorges Dam, which is 22.5 gigawatts of energy is generated through hydro. This has 26 machines of 700 MVA. Then we go to combustion machines. Combustion turbines are used. They go up to generally 300 megawatt. Diesel generators, they go up to 50 megawatts. And wind is 7 megawatts. I've seen 9. And then the latest one that is getting built for offshore is 12 megawatts. And then geothermal can go from 3 to 130. They are all aggregate is total amount. That is what that 130 tells. And tidal is about 1 megawatt. These are all dated material. You can go back to Google and search, and these might change as the time progresses. Then another thing I wanted to tell is wherever I have got these red marks, they are updates from the previous slides. So if you have the slides which is downloaded and printed from the website, you can make sure and then you can update this. And hopefully we will be able to upload these updated slides onto the CUSP website. Now, after we generate power, transformers are used. This is a device which steps up or steps down the voltage. At the generating station, we step up the voltage and transmit it over long distances through transmission lines. So the power is √3 V times phase-to-phase times current. That is essentially three-phase power that is flowing on that. So as the voltage increases, the current reduces. That means the current through the wires is less. That means losses are less. So if you want to reduce losses, you have to increase the voltage and you can push same amount of power with reduced losses. So that is the main purpose of using a step-up transformer at the generating station to step up the voltage. Three-phase, it could be a three-phase transformer, or it could be 3 sets of single-phase transformers. The larger the size, the most likely they will go with 3 single-phase transformers, and they might have 1 spare extra unit. In case of failure, they can replace only that failed transformer. It provides better reliability. The largest I have seen so far is about 800 MVA. And again, as I mentioned, this could be dated. You can search on Mr. Knowledge, Google, and then you can get a good idea about what is available, what is the largest manufactured 3-phase unit. Now, transmission lines transport power from generating locations to load centers, as I should say, and transmission voltages are up to 1100 kV. In United States, we are up to 765 kV. And then these 1100 kV lines are in Malaysia and also in China. These are the places. And then this could be an overhead transmission system, or they can be cables. Cables are available up to 500 kV. And now we also are looking at DC transmission lines that is up to 800 kV. And then the longest one is in China, which is 800 kV and 2000 kilometers. And also the future trend, as I'm looking at it, is they are trying to build a DC grid underlying in parallel with an AC grid, and that looks to be the future of the industry. So now when we look at it, we have voltage, we have current, and then because it is an AC quantity, it has a frequency. So our intent is to make sure that all these are within specified limits. So we will go through what is available and what are the standards that dictate it, and then how we try to maintain the voltage within normal range, and also we don't overload certain equipment by either because of a short circuit or so we'll take it out. So let's look at the normal voltages. ANSI C84.1 is the one which is used and which specifies what should be the normal operating range at any specified voltage. The voltages they cover is from 100 volts to 1200 kV. Earlier, before this 2011 revision, ANSI C84.1 was limited to 230 kV, and then there was an IEEE standard 1312, which covered from voltages about 230 kV. This was only a short 6-page document, But now they combined and they put everything in C84.1, and 1312 is now withdrawn. And now 2011 version of C84.1 goes up to 1200 kV. The classifications, low voltage, they classify up to 1000 volts, medium voltage 1 kV to 100 kV, high voltage 100 kV to 230 kV. Extra high voltage is 345 to 765 kV, and then ultra high voltage is up to 1100 kV. And the one which I have crossed out here, these were in the older slides that were, and then which was developed long back, and this is the updated version of that. Yeah, electrical systems are designed to operate within this normal range. As per C84.1, they define two ranges, range A and range B. Range A is the normal range it is supposed to operate. And suppose if the voltages get into range B, how do we get into that? For example, a line was heavily loaded or a generator was heavily loaded, and suddenly you lose the outlet, and then the voltage suddenly goes up. Or if it is a long line which was heavily loaded, the voltage was low. As soon as the voltage is taken off, as the load is taken off, the transmission line acts as a capacitor and the voltage shoots up. So if that is in range B, because of changing operating situations, it might go into range B, where we are supposed to take corrective actions within a specified time to bring these voltages within the range A. Now let's look at what is the range A requirement. The maximum voltage then range A is plus 5% of the nominal voltage, whatever voltage level it is. And the minimum varies from minus 2.5 to minus 5%. For example, if you have an outlet here, 120 volts, it can be within 114 to 126. And then in 13.8 kV, it can go from 14.49 to 13.46. The minimum range sometimes varies depending on state regulations at lower voltage levels. So you have to also look at state regulations or requirements if you are looking at the lower voltages. And then if you are serving a customer, the utilization voltage range at the customer cannot go below 90% of the V nominal. This is how they have defined it. But please do go and look at C84.1 or the state requirements, and you will know what are the minimum levels that is allowed in your region. The maximum voltage is up to 5% for voltages up to 345. So if you have 13.8, you can say 1.05 per unit times 13.5 would be your upper voltage. 345, 5% of that is 362. But as we go to the next level of voltages, 500 kV, the maximum voltage is 550 kV, 765 kV is 800 kV, and 1100 kV is 1200 kV. As I mentioned to you, the highest voltage in the United States is 765 kV. Now we looked at the voltage, and that gives you that if the voltages are outside range A, we have to take corrective actions to bring it back into the range A. And then if we cannot do that, then we have to take the equipment out of service. That is what we do with protective relays. Now, when we look at the current, there is another parameter. Conductors or tubular wires are rated to carry a certain amount of current that limits the temperature rise to certain 30 degrees above ambient. I think, let me look at this here. Yeah. Now, if you look at this, typically, if it is a transmission substation bus, then they say it is 30 degrees over 40 degrees rise, ambient, 30 degrees rise over 40 degrees, that is 70 degrees. And off late, we have gone up to 85 degrees under emergency conditions. Now, if you look at the transmission line, there are various conductors. It could be copper conductor or aluminum conductor or aluminum conductor steel reinforced, that is ACSR, which provides them the mechanical strength. And based on those, the maximum operating temperature changes. Copper and aluminum, they're 85 or 90 degrees, 85 degrees, I think, is the maximum allowable temperature. And then under emergency, they allow for certain amount of duration, over 100 degrees also. Then ACSR is aluminum conductor, steel reinforced. They operate around 75 degrees, and then under maximum allowable temperature is 100 degrees centigrade. There are other types of conductors, aluminum conductor steel supported, ACSS. These are up to 200 degrees they can go. And then the most, the latest one is aluminum conductor, composite conductor, that is ACCR from 3M. They can go up to 210 degrees under as normal operating temperature, and the maximum under emergency, they go up to 240 degrees. What does it mean? The current that is going through the conductor is the one which causes the rise in temperature because of the resistance of the conductor, right? So now, if I can tolerate higher temperature, we can push more current. So ACCR is now considered in a lot of places where we have to push more power through some regions where we cannot go back and then add extra lines. For transformers, we look at the oil temperature, top oil temperature, that is defined as 65 degrees rise over 40 degrees. As we keep on loading the transformer, the windings get hot and they are cooled by the oil, and that oil, hot oil goes to the top, and we monitor that, and that cannot exceed 105 degrees centigrade. The currents and voltages, we know what are the limits. The voltages are the range, and currents, it is the temperature rise that limits it. And then if you come to frequency, this is very tightly monitored, and these are 60 plus minus 0.5 hertz. There are regional requirements for corrective action if the frequency is outside this. One good example of this, those who are working in the industry, they know that they have under frequency load shedding. So if there is load is too much when compared to generation, then there is a tendency for the generator to slow down. So to prevent this, what we do is we take off, we shed the load to match the voltage load and the generation, and to bring back the frequency to the normal range. Normal operation. So normal operation as defined by Mason is that it assumes no failures, no mistakes of personnel, nor acts of God. So there is no such system as a normal system, because there will be some kind of contingencies which allows this to go out of range or get their current limits exceeded. So we have to design the system that should take into account the failures or system configurations, or human errors. By mistake, we open some line and then it causes problems, or abnormal operating situations. So we design our system so that we can take into account all these failures and take corrective actions. And this is mostly done by relays and the controls systems. Electrical failures, if you look at it, if there is a lightning, then it hits a transmission tower, the voltage rises on the tower, and there could be a backflash, as they call it. It flashes over from the tower to one of the phases that is energized. And then even a station also, we can get switching surges when you operate some, it's just an L and C circuit. Most of these are inductive and capacitive circuits, mostly inductive in electrical system. So whenever you interrupt currents, you get transients. These are high voltage transients, and surge arresters are the ones which are used to limit this voltage. If there is sustained overvoltage, 60 hertz overvoltage conditions, we have relaying, which looks at it and then take corrective action. Then short circuits result in excessive fault currents. If that happens, then we have fuses which disconnects the circuit, or relaying to detect such conditions. Relays just monitor the voltage and current and take a decision based on whether it is normal or abnormal, and they operate devices They are circuit breakers or circuit switchers, which can interrupt very high fault currents. Then we have a severe unbalance of generation and the load, as I mentioned before, that leads to an off-nominal operation. So you have detection schemes to mitigate these situations. You have frequency relays, or if there was a fault, when you clear the fault, then there will be oscillations in the system, and that might put all the generators are in synchronism. Then one might go out of synchronism. Then we use out-of-step blocking or tripping schemes. We will talk about all these schemes later in this. I'm just introducing these terms here. And then we have severe over voltage, under voltage conditions because of imbalance of load and generation. And the voltage relays are used to isolate load and equipment under such conditions. So we have fault situations, we have abnormal situations. Both of them are addressed with relays taking control actions to make the system normal again. So protective relays detect short circuits and or abnormal operating conditions that may affect the equipment or the system. And what is the purpose of the protective relay? It isolates only the faulty equipment. You don't want to have a relay sitting there with happy trigger, and if as soon as it sees a disturbance, if it operates, then you will have probably a blackout or no power for a wider area than what is required. So the relays are designed, the relay systems are designed so that it takes away and isolates only the faulted equipment or faulty circuits. Now let's look at a simple generator, which has got a generator breaker and a step-up transformer, and then that is connected to the rest of the system. So now when we look at, suppose if there is a fault in the generator, what do you think should operate and open the circuit? Obviously, it is the generator breaker. So what the relays does is, as soon as it detects that there is a fault in the generator, it opens that particular breaker. Now, as protection engineers, we cannot just rely on one equipment or one device detecting abnormal condition and then isolating this. So when we ask the question, what happens if the relay does not operate? What do? We have to put a second set of relaying, or we have to make sure that there is some other relay which is sitting farther away and looking into the generator and takes care of this. So the second set of relaying is called a primary and secondary relay, or a main one or main two relays. The terminologies are different, and sometimes they use primary and backup. And backup generally was associated with slower speed relays, and but most of the protection units sometimes use this in a loose sense that they might operate in the same at the same speed. The backup relay essentially is some other relay sitting farther away and looking into the system, and it detects a fault and says, "Oh, something wrong, something happened here," and it waits for some other relay to clear it, the primary relay. If it doesn't operate, then it operates after some time. So backup relayings are generally time delayed. Now let's look at it if the breaker fails to operate. So now if the breaker fails to operate, we have to provide some device to detect this condition and then make sure that all the adjacent sources of the fault are disconnected. This could be at the same location, or this could be at the remote location. So now we had a fault on the generator. We had primary and secondary relays sitting and monitoring the system, looking into the generator, and both of them decided that there was a fault. It sent a trip command to the breaker. There is something wrong with the breaker, and the breaker did not open. What we do is we tell another relay that is monitoring the current through this device, and we call this a breaker failure relay. What it does is, if the current is going through the breaker, and if it knows that this breaker, there is an open command sent by these protective relays to trip this breaker, then it knows that the breaker has gotten a command to open, and it is monitoring that. Breakers' operating times are typically 2 power cycles, that is 32 milliseconds, or 3 power cycles, which is 50 milliseconds. And there are in legacy relay breakers are there, which can take 5 cycles or 8 cycles. Most of them are gone. Most of the modern relays or modern breakers are 2 cycles or 3 power cycles. So this breaker failure relay knows that there was a trip command sent to the breaker, and it starts a timer. And this timer looks at 1 cycle, 2 cycle, and if it is a 2 cycle breaker, it should have opened. So we give a margin, 3 or 4 or 5 cycles, and it knows that the breaker did not open. When this happens, what it does, it goes back and opens the high side, other source. The only source that is connected to the system is this breaker on the high side of the transformer. It opens that. So breaker failure relay essentially monitors the current through the breaker, and also monitors what are the open commands that are going into that breaker. And if the breaker doesn't open in a certain specified time, then it clears all other sources. In this case, there was only one other source, which is outside. And an interesting thing here in this example is we have taken a fault on the generator, which is a huge rotating mass. So if there is a fault on the generator like this, then even if you open the breaker, the fault current is fed to the fault because it is rotating, and then you can expect extensive damage in the generators in this case. Whereas in other cases, as soon as you detect a fault, you open it out, you cut off the current that is fed to the fault, and you might reduce the damages. So now here is a breaker failure. We could have done another thing also. We could have put a relay which is sitting on the bus side. We call it a bus side of this main breaker, high voltage breaker, and looking into the generator, right? When it is looking into the generator, then it knows that there was a fault, and it knows that something should have cleared it within about 2 cycles or 3 cycles. We can wait for about 7 cycles or 8 cycles and say, so nothing got cleared here, and then we open this breaker. So essentially, for the same problem, we have 2 solutions here. So that is why protective relaying is something which is an art. There is no one unique solution. There are many multiple ways of solving the problem. The advantage of using this backup relay here was that we don't need a secondary protection on the generator, and we don't need a breaker failure. That purpose is taken care of by this relay. But the disadvantage of this is if the primary relay has failed, it takes 7 or 10 cycles for this to operate, for a 2-cycle breaker operation. So now the other things which we use in a station, other than the AC quantities, are DC power that is required to operate these huge switches, and also auxiliary devices. That is, for example, if we have an auxiliary relay, just to multiply the contacts, we need some other power to operate it. We typically use DC. Generally, these are provided by, there is a station battery which supplies power to all these devices. And then the solution is to provide remote backup or provide redundancy back in case of a battery failure. There are critical stations where we will have 2 sets of batteries, and then these are providing 2 separate paths, as I mentioned it here, for primary and secondary redundant paths. So if one of them fails completely, then you can still operate. And then suppose if there is only a single battery system, if it fails, then nothing operates at the station. So you have to give protection from the remote ends to take care of any problems within the system. The other equipment which we use for relaying is current transformers. I mentioned to you that you have 800 MVA, 23 kV or generator. The current is around 20,000 amperes. You cannot have the current getting into some device to monitor it. So what we do is we step it down. And for example, in this case, it is 2,000 amps. was the current of a generator here we have taken. And this is a very small generator. If it is 800 MVA, it will be 20,000 amps if I take that. So you will have the primary current scaled down to 5 amperes that is fed into the relay. So if I measure 5 amps in the relay, it is equivalent to 2,000 amps or 20,000 amps, whatever circuit it is protecting or it is monitoring. So these current transformers are very important for us. In the next segment, we will go through what it does, and then we will look at it also. The other thing we need also is a potential transformer. So it steps down the voltages, primary voltage, to manageable levels, that is 66 volts or 120 volts. So these are very common. You need a potential transformer and a current transformer, and they feed the required information into the relay to make appropriate decision. So that was covered in the first module that is there on CUSP website. And now we will continue with the second one. And then we will talk about what are the inputs of current and voltage inputs, and then how these relays are classified in this section. I will go through this little faster. These are all introductions. You can spend time looking at it on the website, the CUSP.
There was a question.
Yeah.
For the first module, there was a question. We go to more and chat.
Okay.
Yeah.
There is a question. I clicked on it. I couldn't see the question. That is why.
Okay, can you stop share for a second?
Yeah. Okay. Then I can share that, right? This one. Yeah, there was a question on what is the longest time for the breaker failure. Many I have seen, if it is a 3-cycle breaker, they used to give maximum of 12 cycles, 18 cycles, as I have seen before. But as we are getting more consistently operating breakers, they are given, for example, if it is a 2 cycles breaker, you can have 5 cycles as the operating time. It depends on your comfort level. And most of the times, if the system allows the fault to stay there for a longer time, then they allow this time to be longer. But faster the clearance is better for us. Whereas in case of stability related issues, we try to keep it as low as possible. I have seen a 5-cycle breaker failure for a 2-cycle, and we have seen 7 cycles also on a 3-cycle breaker. And also sometimes based on the type of fault, whether it is a 3-phase fault or a single line to ground fault or a phase-to-phase fault, the severity of these faults is on the stability is considered. And for a 3-phase fault, you will have a less breaker failure margin given. And for a single line to ground or a phase-to-phase fault, they give a little longer time delays. So now coming back to the relay input, we said that current with 5 amps as a nominal input. This is in the United States. If you go to Europe, there is 1 ampere. And then nominal voltage is 66 volts to 150 volts. Most of the electromechanical relays could not handle more than 70 volts. That nominal the taps that is available on a potential transformer is 69 volts secondary, or 115 volt, 115 volts secondary. But later on, as we have progressed, microprocessor relays went to 150 volts. Then right now, I think it is about 300 volts continuous. So it doesn't matter whether you have a tapped voltage or not. You can connect a full voltage in all the modern relays, because most of the relays available now can take 250 or 300 volts. Now, derived quantities from the voltage and current is frequency and impedance. Impedance is nothing but the ratio of voltage to current. and that can be computed with two inputs that is fed to the relay. Other concept which we have to be very much aware of are the zones of protection. So now let's look at this first one. This was, if we have a generator fault, what is it that we are operating? We are opening only this particular generator breaker. This is called generator protection zone. Similarly, if you have a transformer fault, then we have a transformer protection zone, which any relay that operates detecting a fault within a transformer opens the high voltage side and low voltage side circuit breakers. And then in the larger generators, you never have a breaker on the generator because, as I mentioned, 800 MVA, the current from the generator is 20,000 amperes. If you have 20,000 amps, it is very difficult to have a small mechanism to operate. So generally, they have they connect directly to the transformer, and then they put a circuit breaker on the high voltage side of the transformer. Then the generator transformer is considered as one unit, and that is why we have a unit protection, which is monitoring both the generator and the transformer. The next one is bus. Bus is just a junction where the generator and then all the lines, other lines, it can be one or more generators, they're all connected together. And then if there is any fault at this junction, the bus, we call it a bus, then we open out all the breakers. This is called bus zone. And similarly, we have transmission line. I'm showing only where we monitor the current coming into the transformer and going out of the transformer. So this is a differential sort of a protection. We will talk about this in the later slides. And then we have a shunt capacitor. We have a zone for that. When a fault occurs, when there is some abnormal situation occurs, a situation is detected in shunt capacitors, we open only the shunt capacitor breaker. Now, if you look at a shunt reactor, it doesn't have a breaker. So whenever there is a shunt reactor problem here, the two isolating devices are the transmission line breakers. We trip it out, and it becomes part of the transmission line as a zone of protection. So when you look at this, we have a generator zone, you have your transformer zone, you have unit protection, bus protection, line protection, shunt capacitor, and shunt reactor. So boundary is defined by the fault interrupting device and the location of the current transformer. Let's look at it in more details. We have current transformers, and then we have the breakers within this. For a bus, you have a breaker, and then you have a CT, which is on the line side here. And here there is another CT on the line side. Here it is on the transformer side from the GSU, from our relay. See, whenever a fault occurs in the bus, we open these and then take care of this. So this is the zone of protection as we defined. Sometimes it is not possible to have CTs on both sides. And we try to include the interrupting device within the monitoring circuit. What I meant is the CTs are outside the interrupting devices in an ideal protection zone. This may not be. Let's look at another aspects here. When you look at this, this particular zone protection, what do you find? That generator protection, this breaker, which is connecting generator to the transformer, that is, if there is a fault within that, transformer protection relays also operate as well as the generator relays operate. So there is no blind spot here. So you don't want to have any blind spots for operation. You don't want one relay telling that it is not in my area and other relay telling that it is not in my area. So it is very important for us to have these overlapping zones. This may not be possible all the time. For example, we have one set of breakers called dive tank breakers. The interrupting device is sitting on an insulating column, and then you cannot have transformers on that. So you either put it on only one side, either on the bus side or on the line side. Here in this case, if I have a bus, this CT, which is connected to the bus protection, that the breaker is outside this zone of this monitoring point. So if there is a fault between the CT and the breaker, then what should operate here? If you look at it here, it looks as if it is outside the bus zone, so the bus relay will not operate. And then the CT, the line relay, which is looking on this towards the line, will operate. But if it opens the breaker, still it is fed from the generator here. So this is a blind zone here. So what we do under such conditions is that you try to trip both the zones, which are where to prevent these blind zones. Other modern relay solution is they make use of the status of the breaker and disable that CT input to the bus. So when you look at it here, as soon as this breaker is open, they just take away this current that is fed into the bus relay. So if a fault occurs here, these two currents are coming in, and that shows an unbalance and the bus relay operates. So these are different methods that is available in modern relays. Now, the other challenge which a protection engineer sees most of the time is if there is an equipment that is not performing as desired, or there is some equipment failure, then they have to go back and reconfigure the system to allow the operation. For example, if this generator breaker is a faulty thing, we can't have this open until we repair this. What they do normally is they bypass this, they take an outage for the whole thing, open breakers 2, 3, and then put a jumper here or put some connections which bypasses the breaker, isolate the breaker, and then re-energize and then make use of the generator. So if you do this, then all our zones of protection is gone, right? Now, 2 and 3 breakers are just serving as main unit protection breakers for generator and GSU. So you have to expand the zone. That means your CTs of the 2 and 3 are connected to this protection. And also, breaker failure initiates have to change, and you have to make sure that these are taken care of. Other names that are used sometimes is MRS price protection. I have not seen anybody use in the United States, but outside US and UK, this was a common name that was associated with these zones. And unit protection, and also it is a differential protection because it is looking only in a blind spot, looking at the current coming in and current going out. So protection zones must be not clearly defined. Also, there are other ways of protection. For example, if I have an overcurrent relay sitting on a transmission line looking and monitoring the flow on the line, and that means it is an open-ended thing. If the fault is on the line, if the fault is on the remote bus, or if it's on the high side of the transformer, the short circuit current continues to flow. There is no not clearly defined zone. It is called a non-unit protection. And then the other relay which is used, a transmission relay, is impedance relay. It looks at the ratio of the voltage to current at the relaying at one location, one end of the transmission line, and makes a decision whether there is a fault on the line or it is a normal system. So these are these are called non-unit protections where the zones are not clearly defined. Now we'll look at this slide here. If this just gives an overall picture of how a protection engineer should have designed this system. Normal operation clearing for generator fault is number 1. If it fails, I have to open number 2. And then generator step-up transformers, I have to open 1 and 2. If the 2 breaker fails, then I have to open 3 and 5. And then I have listed down all this. Couple of homeworks that is listed at CUSP also go through this. Because we are just introducing you to the concept, you can spend time and then make use of those homeworks and then work on it. And if you have any questions, you can email me or send it back to CUSP later on. So essentially, relays detect short circuit and abnormal conditions or abnormal conditions. and they take corrective actions by isolating the equipment to prevent the damage. So now the electrical parameters are also used, associated in designating relays, voltage relays, or they look at over voltage, under voltage, or rate of change of relays, or rate of change of voltage that can be used. Similarly, current also, there are over current or under current or rate of change of current. Phase angle is used for the directionality of the fault, whether there is a fault on the transmission line or fault behind the transmission line at the relay location. They look at the phase relationship between voltage and current, or between two current at the inputs at both ends, or it could be at the same end also. And derived quantities are voltage impedance, as I mentioned. It's the ratio of voltage to current, and they use rate of change. This is used in auto step. Frequencies, they use over voltage, over frequency, under frequency, or magnitude or rate of change, volts per hertz, or overfluxing. And harmonic wave shapes are also used in transformer protection. Relay classification, when we look at it, we have electromechanical relays. That was the only one till the 70s, early 70s. Then we had static relays, and then we had numerical or microprocessor-based relays. So major developments of electromechanical relays was done in 50s. Then solid-state transistor was invented in 1960s. And then we had static relays, solid-state relays, as they call it. Then we had op-amps and CMOS technology, early 70s. Then microprocessor-based relays was in early 80s. This became, and most of the relays now are digital relays, which are microprocessor relays. Then they are on the type of the electromechanical relays. They had different types. One was a telephone type relay, hinged armature relay, clapper type relays, or plunger relays, induction disc, induction cup. This is just from a historical perspective, but you have to know that there are still a lot of relays in the system, which still have a lot of them in service. So that is why we just indicated here. Now let's look at the fault current. We looked about the types of relays and classification of the relays. Now let us look at the voltage and current under fault conditions. The system is mostly inductive, what we look at it. And then if a fault occurs, then the inductance does not allow sudden change in current, right? So the fault current is given by a steady state current, sinusoidal current, plus a transient value, which is decaying, e to the power of minus alpha t. And then it has a multiplier sine theta minus phi. Theta is the angle at which the fault occurred. That is the angle. And or the breaker is closed on a faulted line. That is the angle. And phi is the system angle, as you see. So it depends on the incidence of the fault on the voltage waveform. So, and then when you look at this voltage at the relay, if you go through the equations, then you get similar sinusoidal component, and then you have a decaying component, but the decaying component gets multiplied by another sinusoidal term, phi L minus phi. Phi L is the line angle, and phi is the system angle. They are generally very close, so we will talk about it in the next few slides. So now when a fault occurs, depending on the angle, if this is the steady state current, and then at the time t equals 0, if there is no current flowing on the line or in the equipment, then at time 0 plus, time t equals 0 plus also, there should not be any current. That means you have a steady state current here. If you move it back to the point of inception of the fault, then it would have gotten some value here. So I should generate a transient decaying component which cancels out this, so that the resultant current is starting at 0 because the current before the fault was also 0. So we have a decaying component which is shown here. So the current input may have a DC offset. The amount of offset depends on the fault incident point on the voltage waveform. Typical line angle is about 60 to 85 degrees, and generator is 80 to 87 degrees. Overall system angle is, I should say that it will be more than that. It's about 85 degrees. and it varies with the location where the fault is, right? And then in voltage inputs rarely have offsets, as I mentioned, because phi L is very close to phi. If these two angles are same, the in angle and the system angle, then it is considered as a homogeneous system. So that is why we don't talk about DC offsets in voltage inputs. We always talk about DC offsets in current inputs, because the angle of inception of the fault determines the amount of offset we get. What does it have? What does this DC offset affect in relay operation? If it is electromechanical, like attracted armature, the plunger pulls an armature depending on the amount of flux. So this is very prone to operation with an offset. Then if you have induction disc, like our electric meter, they are not affected by that so much, because the two fluxes which are sinusoidal, and then they won't get affected by the DC. Static relays, they have filters designed to remove these. In microprocessor-based relays, we have different algorithms, X1 minus X2 plus X3 minus X4, 4 samples, and the DC gets canceled out in these 4 samples. And they also have mimic filters. These are essentially the same as for the currents. The current is going through a mimic filter, the voltage that is developed across is generally don't have any DC offset, because that the impedance through which the current is sent has the same time constant as the line time constant. And use of transactors also reduce this. Then we have relay types based on functions, overcurrent relays, differential relays. You can read through this. Directional relays that respond to phase angle, and distance relays. We did cover it in the previous few slides. Now, if you want to create a diagram, then if you want to keep on writing as distance relay, voltage relay, current relay, it becomes a problem, or it clutters the diagrams. So we use device numbers. This is defined by American National Standards Institute, ANSI, or IEEE C37.2, where they say a time delay relay is 2, distance relay is 21, overcurrent instantaneous is 50, if it is a time overcurrent is 51. Circuit breaker is represented at 52, differential relay as 87. Please look through this standard, and that is what we use. These are the numbers that we use in any representation of in a diagram. And relay system design for a system, what we need to know is we should have a system layout first, and we have to determine the CT location, define protection zones to minimize outage, to remove only faulted equipment, as we discussed this, and determine the redundancy, second relay or a backup relay. Make sure that there are no blind zones. I'm just going through a little fast because this is more useful in the next few slides. You show the location breaker and CT, show relays connected to CTs and primary or backup, show which breakers are open when the relays operate. Alternate names for these kind of diagrams are called metering and relaying diagram, or single line diagram. And then based on past practices, these designs are based on past practices of utilities or power plants, varies from one company to another. Some utilities show what are the CTs and PTs connections on one sheet, and some show on tripping logic. This has not made sense to you, but I will show that in next slide here. If you look at it, I have 2 breakers, and then that is connected to a transformer, and there is a breaker on the low side. So what we do is, here is a bus from 52-1 to -2 to the transformer that is protected by a differential relay 87B1P. And when it detects a fault in this region, what does it do? It trips 52-1, trips 52-2, and initiate a breaker failure on 52-1, initiate breaker failure of 52-2, and initiate breaker failure of 52-3, and that is also tripped here. So these are the corrective actions, what it takes as soon as it detects a fault. And the CTs to monitor this particular bus are fed from the line side of this breaker, line side of this breaker, and the transformer high side here. Similarly, for a transformer differential protection, we connect it like this, And then we have 52-1, 2, 3, and then we initiate breaker failures for that. See, this is what I meant. You should have a first layout of the system, what you have, and then you find out, locate the CTs on what is available. Then you connect them to make sure that there is no blind zone. Here, for example, if there are CTs, 4 CTs on the high side of the transformer, the outermost CT is connected to protect the transformer. The innermost CT is connected to the bus. So if there is a fault within this column here, then we don't have any blind spot. And you can go through this and you will see how they are connected. This is the basic concept of developing a relay protection diagram, which is metering and relaying diagram. Other example in the feeder is you have a feeder with a current limiting reactor, and then 13.8, you have one of the manufacturer relays, and then these are functions which are used in it, that is shown here. And it has a reclosing unit, and that is done by a PLC. So what has changed in these designs? Electromechanical relays were single phase relays, and one relay did each function. And then solid state technologies, they combine 2 or 3 functions in one. So you could have under voltage, over voltage, over current relay, or a distance relay in one package. When we came to microprocessor based relays, they became multi-function relays with emphasis on fault recording and control features. And earlier, whenever a fault occurred, they went and looked which relays operated, and it was the imagination of the protection engineers to figure out what actually happened and recreate the scenario to, like Sherlock Holmes, to figure out what went wrong. But nowadays, a picture is worth 1,000 words. You get a nice fault recording, and then you can look at it and make a decision, then find out easily what happened. The latest technologies that is being used, and this is wide area protection, synchrophases, and interoperability standards, that is 61850, that is a communication-based protection schemes where they exchange information. That is the future, and then that has changed from single function relays to microprocessor-based relays. What is slow to change? Protection application philosophies is based on the equipment. So if I have a guy who has worked for 20, 30 years, and he has only seen electromechanical relays, when you get a microprocessor-based relay, he's hesitant to put all the eggs in one basket, different functionalities that is available. So majority is still based on electromechanical relay concepts. Several multi-function relays are used as multiple single function relays. But this is changing very fast now, and they are trying to take advantage of what is available in the microprocessor relays. The cost of implementation of new concepts is easy, but prevalent legacy approach blocks such changes, citing additional maintenance overheads. Now, for example, if I want to protect a generator, you get one box which has all the functions. You can use it on a small generator or 1,000 MVA generators. You can put the same box and then enable functions that are required for that. Earlier in electromechanical world, each functional was one box. So if you want to have more functions, we were putting more boxes. So depending on the criticality of the equipment, we were adding more functionalities. So the designs, they used to use single function, that they were not redundant functions at lower voltages. And then as the voltages increased, and then criticality of the equipment increased, they tried to add redundant relays and additional functions. So the cost of relaying was higher at higher voltages than compared to lower voltages in the electromechanical world. But now with microprocessor, it is the same box. You can just enable and disable different functions that is required. So the cost of implementation of new concepts is very easy. Mostly based on past experience, these are for protection designs. There are many ways to provide redundancy, local or remote. Unlike physical layout designs, different solutions may not have significant effect on cost projects. In the case of physical design, if there is a major problem in design, there is a major design error, it takes a lot of money to fix it. Whereas in the case of control schemes, you have a microprocessor-based relay. We have not set something, you can go back and rechange and do that. So the cost is not much. So that is why sometimes, control engineers are blessed that their impact is heavy, but they can go and fix a problem by rewiring some terminals or reprogramming the relays. Whereas in physical designs, it is, if something is wrong, it needs to have another pillar built, or you have to pour concrete somewhere. It costs money, quite a lot of money. As I mentioned earlier, it is more an art than a science, protection engineers. So no two utilities have similar philosophies also. They vary quite a lot. But the essential philosophy is, if there is a fault, you have to clear it as soon as possible. And then if there is a failure of a protection equipment, there must be some other way to take care of this and account and provide backup protection or redundancy as required. Other terms used in relay world is, we talk about sensitivity of the relay, selectivity of the relay, reliability, and security. Essentially, selectivity is operated as intended. If you don't want the relay, to operate, then it should not, and then that is selective. Reliability is, it should perform when called upon. In the previous world, and several years back, 20 years back, it was insisted that a protective relay has to operate, even if it is misoperates and clears, it is okay. But now it is not true. You cannot misoperate, you cannot trip a circuit if there is no fault on it. It is equally important that we give security, selectivity, very important. It becomes an important aspect in all the designs now. We also cover in this, in the next 2 days, auto restoration. Suppose a fault occurs. Most of the faults are temporary. Sometimes a lightning or an arcing occurs. You can disconnect everything and restore it. And then they have alarms to assist system operators' decision. So this, with this, we will stop here for about 10 minutes. Then 9:45 or 9:50, we will start again.
videos.
Yeah, this one. Now let's see. Zoom. Let's start. Share this first.
Before that, if you want.
What's the one, right? Okay.
You can go to slideshow.
Okay. Good morning. We will start the second session now. We talked about relays, introduced the concepts of primary, backup, redundant schemes, and then we also looked at how to create a single line diagram or metering and relaying diagram to understand the concepts. And this metering and relaying diagram is used later on to develop the actual the schematics that are required for the maintenance and construction of panels and others. This is for those who are practicing engineers. This will be useful, but if you're students, then it might be, you may not figure out what it is, but you will learn later. Now, in the second session, we'll talk about instrument transformers. As I mentioned, that these are required for stepping down the voltage and current to manageable levels that is fed into the relay for monitoring. So current transformer steps down high currents to relay input levels. Applications are, this is for metering and relaying, we use this. And there are different types of CTs, bushing CT, freestanding CT. We will explain all these, auxiliary CT and optical CT. So now the transformer fundamental concept is voltage times power on any primary side. It has got number of turns is NP and NS on the secondary side, and the voltage and currents on one side is related to the other side. The product of those two must be equal. That is, total power coming into the transformer is equal to power going out. Of course, there will be some losses. Let's not look at this. They are insignificant when compared to these numbers. And similarly, the other one which any magnetic circuit has to satisfy is ampere turns. They should be balanced. The current times the number of turns on the high side must be equal to, on one side, primary side, should be equal to current times the number of turns on the secondary side. Or we can look at it here as IP by IS. The ratio of primary current to secondary current is same as, is inverse proportional to the ratio of the turns. That is, IP by INS equals NS by NP, and the voltage is directly proportional to the ratio of the turns. So now if I take apart voltage transformer, when I apply the voltage here, if there is no load connected on the secondary side, what it needs is some current, call it magnetizing current, that is to keep the flux flowing through this magnetic circuit. And that it takes certain amount of current, IM, which is generally about 1% of the full load current. And then if we start loading it here on the secondary side, the primary current will be NS by NP times IS. IN, I know that ampere turns should be equal. So it gets transformed. The lower the voltage on the secondary side, higher the current on the secondary side is. And if you transform it, then it comes back as IP is NS by NP times IS plus IM. With the secondary open, it takes only magnetizing current, as I mentioned. If I short this, then the whole current is limited by the impedance behind this source. So it can be much higher. It is about 10 to 15 times higher than its normal rated value. So that can result in damaging the transformer too. The current transformers are a little different than voltage transformers. Here, the primary current is not decided by the secondary current as in voltage transformers. This is connected in a circuit, and the primary current is determined by external load that is flowing through this. And because of that, it produces some voltage across this to push the current through a burden. So if I have a shorted secondary transformer here, current transformer, the ratio of the currents is IS will be equal to IP by NS minus magnetizing current. So it will be same. Then as we start putting some impedance connected to the secondary side, it starts developing voltage to push the required current through the impedance. This impedance is called the burden in the case of the current transformers. Suppose if I open circuit, what happens here? There is no load, and then the voltage tries to increase quite a lot, tries to push current through that. That means if you have an open circuited current transformer, you get very high voltages on the secondary side, which might damage the turn-to-turn insulation of a transformer. So if the current transformer is not used, we typically short it. But if the voltage transformer secondary is not used, it is kept open. It is not shorted. So this is a bushing current transformer. There is a breaker here, a gas breaker, and then bushing CTs are put slid on the top of the bushing here, and they are at the bottom of this. You might have seen this also. Internally or externally mounted bushings. Internal the bushings, where do we see this? It is in transformers. You have the bushing, condenser bushing, which is going down, and then all the CTs are mounted inside the tank. And whereas in breakers, they're all mounted outside. And then these bushing mounted transformers has got a hump like this. The designation is as shown here. The CT rating, if the primary is not an integral part of the CT, that will be then the CT should be rated for whatever current this primary can carry. This is a requirement. For example, transformer or bushing CT, the transformer loading is the one which determines it. The transformer can take excessive load temporarily for a certain amount of time. The CTs also must be capable of taking care of that, allowing this continuous current continuously. We also have freestanding CTs. Where did we talk about this? In live tank breakers. You don't have CTs on the breakers. They're outside. So there, it's used in ultra-high voltage systems. You can see that you have a CT here. This is mounted on an insulator, and the current comes in here and then goes through course here at the bottom, which is insulated, and then goes back up here to this. These are the two terminals which gets connected in series with, in buswork. Then cores can be either at the bottom or at the top, as I mentioned. It depends on the type of the CT manufacturer. And classifications of current transformers, we have metering class and protection class. Metering is we are trying to revenue meter or something where we are trying to charge somebody or monitor the amount of energy consumed. So our interest is from 0 to their rated load consumption, right? So our interest is from up to the full load rating of the equipment. So the transformer has to reproduce the current as accurately as possible without much error, so that we can get the correct, we can build them accurately. In the protection class, we don't care about normal operation. If the fault occurs, the current can be as high as 20 to 25 times the full load current. So our interest is to figure out how we can faithfully reproduce these currents at very high short circuit current values. So they have to scale down, and with a little error, they should be able to reproduce it so that the relays can detect this condition and take actions appropriately. We also have auxiliary CTs. Suppose if we cannot match the exact CT ratio, if we are trying to look at for the bus, for example, current coming in must be equal to current going out. So we may not be able to get the right CT ratio. Then we try to adjust this CT ratio with some auxiliary matching transformers. Now let's look at the metering CT specification. The accuracy is defined at two levels, at 10% and 100% of the rated current at a specified burden. So you assume it is 0.3, 1.0, B 1.0, they say 2000 to 5. the error will not exceed 0.3% at full rated current of 2000 amps with 1 ohms of burden connected on the secondary side. This is how these are defined. But ANSI standard also says that if the CT is loaded only up to 10% at 10% of the rated current, the error cannot exceed 0.6 per unit, double the whatever number that is specified here as 0.3 here. So it is 0.6%. So this is, we are always interested in metering CT specifications from up to the full load current. So for this is used only for revenue purposes. Metering accuracy class is defined like this. You have a parallelogram, you have a magnitude and phase angle error, and then 100%. In this case, it's about 0.3, right? So it is shown like this. At 10% of the current, it is 0.6%. And the burdens also, they define it. What should be, it is resistive or inductive. They have, you can see that it is mostly resistive burden for the metering class CT, 0.9 power factor here. So 0.1, 0.5, and 0.8, they assume that this is the impedance that is connected to that. Okay. Protection class is different that way. They say there are two classes. One is called C class. C is the low leakage flux. The ratio can be calculated. And then T class is where you have to determine the actual ratio at a particular burden with tests. And there is a new class called X class, which gives 1% accuracy at rated current and user-defined accuracy at 20 times the rated current. And this is C57, IEEE standard C5713 provides all the details for this. So you have C class, T class, and X class. In the metering class, we have a 0.3 or 0.1, and then you have a burden at a specified burden that is specified. Whereas in the protection class, we say C, T, or X. And now protection class, C class ratings is given as C and then with a number here. This number specifies that the CT is able to push 100 amperes to develop this voltage through a required burden. For example, CT is 20 times the rated secondary through a specified connected burden. For example, we'll take C800. That means the CT can develop 800 volts across 8 ohms burden at 100 amperes current going through that. So the CT has enough iron in that so that it can develop that much voltage to push the current. So this is little more inductive loads, they call it. This was all designed because electromechanical relays had inductive coils, and that were a little more inductive. So the burden designation was burden one is at 0.5 power factor, it has got 0.5 resistance and 2.3 millihenries inductance at 60 hertz. So this is how they were defining it. But nowadays, all microprocessor-based relays have very low burden, and then you're talking about 1 VA or a few VAs, which is very, very low. Okay. So if you look at this, CT winding resistance provided CT secondary voltage required to push 100 amps through a burden. Let us look at this. CT winding resistance is the value provided by the CT manufacturer. It is 0.002 ohms per ton. Here I want to just go back and tell you that this course was intended for full 6 months, and I am trying to push in a lot of information to you. So please do go back and look at the video and then just try to understand. We are giving you a synopsis or a pretty fast version of this course, and then it will be easier for you to go back and then look at the videos and then learn that. So if my winding resistance is typically 0.002 ohms per turn, so I have a 1200 to 5. What it means, primary turn is 1. So number of turns on the secondary is 240 turns. So the winding resistance is 0.48 ohms. So C400 means it has a 4 ohms burden. Let's assume resistive here. And then at 100 amperes, CT voltage is 400 volts. Voltage drop on the winding resistance will be 48 volts. So CT internal voltage has to be 448 volts to push 100 amperes through 4 ohm resistance, and then with the voltage on the terminals of the CT at 400 volts. So this is how we are defining the CT internal voltage. Normally, the manufacturers, they give you three characteristics which we look at it. Select a CT that develops at 448 10% error, that is your C400, right? So they provide you excitation curves. 10% error at 100 amperes is what? 10 amperes. So here, when you look at this, and then when you look at if you draw a line here, it is not straight here. So you assume that is a straight line. It is difficult for me to drive right on this. You can see that it's 200, 300, 400, 500. Almost 500 volts is developed across the CT terminal CT when you have 10 amps of excitation current. That means if CT is able to push 100 amperes, 10 amperes is used in maintaining the flux in the core. That is what it means. And then CT can develop up to 490 volts or 500 volts here almost. So we also use another term, relay knee point voltage, voltage knee point of the CTs. This is used, it's a term used by relay engineers. And ANSI defines it as a 45 degrees line on this particular curve, below which it is linear, above which it starts, the current, excitation current, the current required to maintain the flux increases as we try to increase the voltage. And then this is 10% error at 100 amperes. This is called the knee point. So when a lot of people talk about the knee point, it is just a 45 degree slope line, which is touching that excitation curve given by the manufacturer. IEC defines it in a different way. IEC says a 10% voltage increase results in 50% increase in current. That is defined as a knee point. IEC also specifies that 5P protection classes P, 5P20, 10P20. And what it means is at 20 times the rated current, it has 5% error. And at 20 times the rated current, it has 10% error. So 10P20 corresponds to what? In our case, it is C400, C800. They are all 10% error at 100 amperes. So that is equivalent to this. IEC has many more classifications of the CTs. They have TPS, TPXY, and GZ. We don't use this here, and you have to go to IEC specifications. The reason why I just mentioned it here is you might have an equipment coming from Europe, and they might be designed for IEC specifications, and they might have a different classification of the CTs. There's another factor which we look at it. One is the C factor, which we looked, or T or X, whatever we have. And then there is another specification called a rating factor. Rating factor determines the overload capability of the CT. Suppose if it is a 2005 CT, and then it has a rating factor of 2, it means that it can continuously carry 4,000 amperes. What it means is the secondary current, it can provide secondary current of continuous current of 10 amperes. A rating factor of 3 allows 6,000 amps primary and 15 on the secondary side. So emergency loading of power transformer up to 160% of the maximum rating, CT also should be rated to allow this overload rating. So essentially, you look for the C factor on a CT and also the rating factor. These are very important situations. Now let's look at the metering CT. I said that if the load is only 10% of the rated load, the errors increase. So what people do is they use a lower ratio CT. Suppose if it is 1,000 amperes is the nominal maximum load, they use a 500 to 5 CT, and then they use a rating factor of 2. Or you can use 400 to 5 and a rating factor of 2.5, or you can have a lower voltage ratio and rating factor of 3. The advantage of using a higher rating factor on metering class CTs is their accuracy remains the same if it is above 100% of the current. So it reduces as the current is below its rating, but the accuracy, the inaccuracies are not increased if the current is above their nominal value. ANSI standard also specifies that you should have 3 taps in a transformer CT. It's used for protection class. So if it's a full winding of 400 turns here, then you will have X1, X5 as a full turns, 2005. Then they ask you to provide 3 more taps, X2, X3, and X4, and the ratios are given here. Now, what is the effect of tapping it down from the full winding? Now, we say that it's a rating factor of 2. The normal primary is 2000 amps. That means secondary current cannot exceed 10 amperes. So now if I use X1, X2, which is only 80 turns, it is 400 to 5, the secondary current cannot exceed 10 amperes. So the primary current cannot exceed 800 amperes. So even though the rating factor is defined in terms of primary, it is actually the current that is coming out of the secondary that limits that. So rating factor of 2 for 5 amp CT is 10 amperes. So at any other tap, the current cannot exceed 10 amperes. This is extremely important for you to know about this. The other thing we'll also look at in connecting the CTs to a relay is looking at the directionality of the flow of current. So as I mentioned, in a bus differential relay, the total current coming into the bus must be equal to 0. So we just add up all the currents. So if you're adding up all the currents, it is important for you to know the direction of the current that is coming into the relay. So here, I primary is coming into H, and I secondary is coming out of X1. So we designate this with a dots or on primary side and the secondary side. And then in the case of you have a freestanding CT, there are many things. They can X, Y, Z, U, W, and V. We can have many cores on the same CT, and designation is given as 1200 to 5. So the key point is you should know when the current enters the primary with the dot, the current leaves the secondary on the secondary side. So this is how you can connect the CTs to make sure they're adding up currents or you're subtracting currents. Bushing designation is also same. You have a humpback here, and then you have a dot convention is used on bushings also. It is important for you to show this on all the circuits so that when they are wiring it, they know they take the right terminals and then wire it to the relay. Now, if I can take an electrical representation of this, we can show that the CT is like this, and you lose some current in maintaining the flux within the core, that is the excitation current, and then you have the cable impedance and relay burden, and cable impedance is also for the return path. If you are using number 10 gauge wire, which is generally used, we use a typical of 1 ohm per 1,000 feet, and I have seen people using 1.2 ohms per 1,000 feet also. That is probably because at a higher temperature, the resistance increases. But you can look at the manufacturers, whatever they provide, you can use the correct number. And electromechanical relays burdens are generally represented as volt amps. Depends on the relay and the setting, and it can be as high as 15 ohms, which is 3.92 VA, 0.5 amps. Or then normally, if it is 5 amperes, it can be much higher, right? Voltage times the current, or I squared R, Z. So 25 times 15.8 will be very, very high. Microprocessor-based relays have very low burden. It doesn't, maximum is 0.2 ohms here. So it is very advantageous to connect a lower burden here. What is the advantages of having a lower burden here? The voltage that is developed across the CT to push the current through the relay will normally be is sufficient, so it won't go into saturation. That is the thing, which we will look at it in few slides. So the steady state performance, we looked at it. We are looking at C class or rating factor, and we also know what would be the current. Now, the transient performance of a CT, we look at it now. The flux in the core is given by integral of the voltage that is developed across the terminals of the CT for the current. And then, as I mentioned, or as we went through the equations for a fault, the DC offset in currents are possible. That is based on the fault inception angle with respect to the voltage. And then fault current may contain DC offsets. So this, we looked at it before, and then the flux tries to build up like this in the relay. And then you have the flux density that is limited by the BH curve given on for a magnetic core. You cannot exceed that. If you go above this, then it saturates. And then there is no rate of change of flux, so it doesn't produce anything on the secondary side. So as flux increases by a factor of X over R with DC offset. So if you know the system X over R, then resultant flux with the DC offset will 1 plus X over R times the voltage. So these, you can look at some of the books which I have mentioned later. They give you the derivations of this. So voltage that is developed 1 plus X over R times the fault current times the burden. The fault is 20,000 amps, X over R 17, CT ratio is 2,000 to 5, and 2 ohms is the total burden. Then if you calculate that, you'll get 1800 volts. If a C800 is used, it can guarantee only up to 800 plus or 900 volts to push 100 amps through 8 ohms burden. But if if it needs 1800 volts, it is not possible to figure it out. So now we will try to look at how CTs, how fast CTs saturate, and will they come out of saturation. This is given by an excellent Excel spreadsheet that is on the PSR Power System Relaying Committee website. And this was developed by Professor Glenn Swift from Manitoba Hydro, and he shared it with the industry. It is a very useful tool for you. And here the slope is this slope here, and he gives an explanation on sheet 2 on what it is and how to calculate it.
They're not seeing that screen.
Huh? Okay. Sorry, I have to share this screen now. I thought when we click it, it automatically goes. Can they see that now?
Yeah.
Okay. Sorry, you were not seeing this. I just clicked the link and it went and opened another Excel spreadsheet, and we were not looking at this. Now let's look at this. The slope at 22 is the value which you calculate here on the saturated portion after the knee point. And this is explained in sheet 2 of this and how to get this number. And if you don't have any of these numbers, you can just go back and use this 22. And Vs is the voltage. If it is a C400 CT, we looked at it, and the voltage was how much? It was almost about 500 volts, 490 volts or 500 volts when I tried to draw a straight line. And you saw that the voltage developed at 10 amperes is what we have to take that. That is about 490 or 500 volts. Let's say it is 500 volts when we put that. And the CT ratio was 1200 to 5. And the resistance of the winding, we calculated as 0.48. And then I put a resistive burden of 4 ohms. And then reactance, I make it a 0. So if you do that, and then X over R of the system was, I took it as 12, and it could be as high as 17. We can change it. You can play around with these and then try to get a good feel of what happens. So then it also looks whether there was some remnants. What happens is when on a BH curve, when current was going high, the flux was traversing from B maximum to minus B maximum. And as soon as the current is taken off, the breaker opens, the current might be sitting somewhere, and then it has a residual flux. So normally it is about 15-20%, is not uncommon, but it is very high near generators where the CT is saturated because XOR of generator, it is highly inductive, it is extremely high, and whenever there is a system fault and then some breaker opens, the current reduces from high short circuit currents to its normal operating current, and it has a high residual flux on the generator transformers because of the high XOR. So if you assume that it has a full flux as its per unit offset, you can reduce it to 0.25 also and play around with this during your time and see how it happens. So when I reduce this residual flux to 25%, you can see that your curve is almost identical with ideal curve. Let us put this as 1.00. So then I can see that. And then per unit base of VS, we can leave it like that. We don't have to put anything. Symmetrical primary fault current is 12,000 amperes. If you increase it to 18,000 amps, you can see that the CT saturates. Here we have a blue curve, which is a fully offset curve from, and then that is the RMS current calculated in the microprocessor-based relay, and the black is the actual current that is going into the relay. Okay, so the blue line here, straight line, is the RMS value, and then black line is ideal RMS value, and black line is the calculated from the real value because of CT saturation. Couple of observations you have to see here. The CT did not saturate at time t equals 0. As soon as the fault occurred, the CT, it took some time to build up the flux in the CT. So you can see that after a certain amount of time, it saturates. When it saturates, what happens? The voltage collapses on the secondary side, and it does not produce anything because there is no rate of change of flux that is required for developing this voltage that is not happening on the secondary side. So the voltage collapses here, then comes down, and then it saturates and remains saturated for some time. And as the DC offset reduces, then you can see that it slowly came out of saturation. So the main characteristics which we will use later in bus protection tomorrow is the CT never saturates at time t equals 0 plus, but it takes a certain time. Higher the current, faster it is. Suppose if I put it as 25,000 amperes here, then you can see that it saturates faster. Okay, so then whereas if I make this as 10,000 amps, it changes and it takes longer time to saturate. So this is extremely important when we will make use of this principle. So essentially, CT saturates after certain time, at some time after the fault incidence, and it also depends on the DC offset, and then it comes out of saturation after a certain amount of time. So the relay sees less current initially because of CT saturation, then it comes back to the original ideal value after a certain amount of time. So if you have used a time over current relay to coordinate with something else, if the CT saturates, what happens? It is seeing less current, so the relay takes a longer time to operate, and then it may not be coordinating with an upstream device, one behind this. We will go through this later on. We will go back. Yeah, you can see the screen now, right?
Yeah.
Yeah. So we were here, we just went through and played around with that Excel spreadsheet. So for those of you who think, those who are in the field, who have some issues with coordination, if some relay upstream, for example, there is a feeder instead of feeder relay operating, the bus relay operated and took out the whole bus. For new people into this area, this looks like it is something you may not be able to understand, but for practicing engineers, you know what I'm talking about. So under such conditions, most likelihood of this miscoordination is due to CT saturation. And sometimes it recloses, and then you will have miscoordination under such conditions also. So we will, when we go through different protection philosophies, we'll go through this. So essentially, the CT saturation calculator allows you to look and then visualize how the CT is saturated. And then if you know the fault current, if you know the X over R, you know how long the relay takes to come out of saturation. So protection CT selection, what do you do? Maximum continuous current for primary rating. Use the rating factor for emergency rating or select emergency rating as the primary rating. Determine the burden, add cable impedance and the connected relay impedance, and then determine the maximum fault current. And if you know the X over R, you can do that. But as I said, it is impossible sometimes to select a C class so that the relay may not, the CT will not saturate. We have to have it will saturate if you have a high X over R. Other factors of CT selection, the maximum current coming out of the CT is going into the relay, right? Relay digitizes these numbers. So this is a dated material. So we used to, at that time when I prepared this, it was typically 100 amps peak on the secondary side. But now I think relays can go up to 300 amps peak. So that is very important for you to look at it. And the second issue was the CT is also, if you have a higher amount of current, the windings might get hot. Earlier in the previous versions in the CT standards, they used to say the mechanical limit was about 100 amperes, or they used to specify some number. The modern CT IEEE standards, they took away that. They give you an equation to calculate the temperature rise because of the higher currents, and limit the temperature to some value, 235 if I remember, but you can look at the CT. Essentially, the CTs can carry higher currents for a short time, and then that is determined by the maximum temperature that it can reach when it is supplying that current. And microprocessor-based relays, the limit has increased now from 100 amps to 200 amps or 300 amps. Please look at the manufacturer's specifications. Will the CT always saturates? It depends on the burden, X over R, and C rating, and also the point of incidence of the fault. And then the best way for you to know is use that Excel spreadsheet from PSRC website, and that would be very useful. Okay, so faults. When will the faults occur? Majority of the faults are single line to ground faults, and the DC offset is maximum is when theta is nearly -5 is 90 degrees. If you look at that equation, it is sine of theta -5. Theta is the angle at which the fault occurs. Then system angle is around 75 to 85. So the fault should occur around voltage 0 waveform. Normally insulation failures occur when the voltage is high. So most of the faults due to insulation failures are occurring around voltage peak. That means most of such faults will not have very high DC offsets. So the DC offset probability is very low for line to ground faults. But some debris coming and hitting that line or hitting an equipment and creating a fault, it can happen at least at an angle which satisfies this theta -5 equals 90. So it can happen. Whereas if you look at three-phase faults, at least one of the phases will have a significant offset. And this can happen in face-to-face faults also. So we can say that the majority of the faults, because of the insulation failure or flashover that is occurring, is at voltage peak, and they will not have DC offsets. And examine the time to saturate using CT saturation calculator, effective current calculated by the relay, you will know that right away. Other types of CTs which we didn't cover in detail are linear couplers. They are nothing but air core transformers with no magnetizing portion. And essentially, the leakage reactance of that particular circuit is used. So they develop voltage across the secondary instead of the current, then that voltage is proportional to the current flowing in the primary. It's like a mutual coupling, and these don't have magnetic cores. Another one is an optical CT, which we have not covered. And if you can look to see a manufacturer's specifications they provide. The great advantage of linear coupler and optical CT is there is no saturation protection, and also the accuracies of optical CTs are extremely high, even at very low current. So if it's 0 to 2000 amps, they are very accurate from very low current up to 2000 amps. But the flip side of it is they are a little more expensive, a lot more expensive than a single one, and you need a digital conversion from that to nominal 5 amps, or most of the modern relays now allow you to connect those digital inputs, but you can look at it. That could be the future of the instrument transformers. Further reading, I have given Mason as chapters 7 and 8, and this is, they refer to that as ASA standards long back. But now you have protection and automation guide also from G, chapter 6 covers a lot of those. So with this, 01. Let me see, it's 10:33. So we will take a break here, and then we will start with the mathematical tools after 15 minutes. Yeah, I just wanted to mention to you that I have been repeating it again and again, that these we cover in 6 months, and I'm trying to cover a lot of them in 3 days. So it looks very interesting in first half of the day, and somewhat interesting the next half of the day. And then by the time we finish, you might be a little more overwhelmed with the overdose of information. But the intent here is to give this to you as a reference, and then you can make use of this to teach your course, or for those practicing engineers to use it as a reference and look back and then read further from manufacturers' catalogs or IEEE standards or other additional books that is provided as a reference in this. We will again reconvene in 15 minutes. That is 10:50. We will meet again. Thanks. Well, good morning again, and hope you're still there. We will start the third session, which covers, just to let you know, we have covered 4 modules this morning, and in about 2 hours, 2.5 hours, I think, with some break. We will cover the next 4 in the next rest of the day. And this is mostly on fault analysis. The intent here is not to make you experts in calculating by hand the fault current or fault voltage. The intent is just to figure out how to model it in the fault programs that is available now, and then or to verify some numbers you get out of a fault program to make sure it makes sense or not. That is the major intent of these next 4 lectures. I'm looking into this. And as I told you, this is just information overload. And then especially after lunch, after good food, they may not go very well also inside. So you just watch this again and then take your own pace and then learn this. These are not for those of you who have already been taken basic 101 basic courses in electrical. The first one is just an introduction to phasors. And then the second one is introduction to symmetrical components. And the third one is how do we model and how to get sequence the impedances from different equipment. And the last one is we take a sample system and then calculate by hand and how they go through, how to go through these calculations and figure it out. So let's start with the first one here. What we cover in this section is representation, polar or Cartesian or exponential, mathematical manipulations, and operators J and A, representation of current and voltages. Then we look into per unit and percent quantities. This is a way to cross the boundaries of voltage levels. As I mentioned in the very first one, it is generator was at 23 kV and transmission was at 230 kV and the distribution was at 13.8. There are 3 different voltage levels. So as you keep on changing current and voltage, they might change. Instead of using the actual voltages and current magnitudes, we use per unit and percent, which is invariant of the voltage quantities. We'll go through that, and we will look at network reduction methods that were available historically. If you have taken network courses in electrical engineering, Van Valkenburg or Balavanian, they would have covered those in those books. And then we introduce symmetrical components. So a vector can be represented as an arrow here, which has an origin as a terminus. And then the position is represented in either Cartesian or polar. And then polar is with respect to your reference. You give the magnitude of the vector, and then you give an angle with respect to that plane. And in the Cartesian coordinates, you have put it as x and y coordinates, and you represent it as x plus jy. And then they are related. R is square root of x squared plus y squared, and theta is tan inverse of y by x. And you also have a trigonometric representation as r cos theta is x, and then sine theta is y, or sine theta is y. The exponential form is you just assume r as e to the power of j theta. J theta is an operator which rotates this vector with respect to a reference by an angle theta in the counterclockwise direction. These are the basic representations of the vector. And then we also have an operator J and A. J rotates a vector by 90 degrees in counterclockwise direction. And it has a magnitude of 1. So if you multiply 2 J's, it is J squared. That means, and if you have a voltage vector here, if you multiply by J squared, you're essentially rotating the vector by 180 degrees. Similarly, we also use an operator A, which rotates a vector by 120 degrees in counterclockwise direction. So if you look at V, then if I want to rotate it by 120 degrees, I multiply this by AV is at 120 degrees from V in the counterclockwise direction. A square V is 240 degrees here. So if I rotate it again after A square, where does it come to? It comes back to V. So A cube is 1, and A is cosine of 120 plus J 120. And Cartesian trigonometric functions, if you allow that, A is minus 5 plus J 0.866. A square is minus 5 minus J 0.866. If you represent it as 4 quarters, the first one is on the first quadrant x-axis, and then the second one is in the second quadrant, and the third one is in third quadrant where x and y are negative, and in the second quadrant x is positive and y is x is negative and y is positive. That is why it's minus 5 plus J 0.866. And other things which we, just for information here, if you have 2 vectors, if you put the terminus to the origin of another vector, and then the voltage across the vector from A origin to the B terminus is A plus B, and the reversal of this is, we call it J squared B, right? If you reverse it minus B, then if you look at it, A minus B is this. And multiplication of 2 exponential terms, product gets, magnitude gets multiplied, but the angle gets added. If you divide, magnitude gets divided, and then the angle gets subtracted. And power roots is Rn 1 over n. These are just mathematical quantities. And relationship between voltages and currents in 3-phase system, voltages in 3-phase system. I have an A-phase voltage here, and then the B phase is 120, and C phase is C. So essentially, how we look at it is, if you look at this arrow here on my this pointer, and then if you look at it, if you rotate it in a counterclockwise direction, A crosses that first, then B crosses it, and then C crosses it, the phasor. So that is how we can represent this. And you see that VAB is square root of 3 times VA. Most of you know, or you can just go through this. Now here, if you look at this, if I move a point on a sinusoidal wave from 0 all the way to the peak, and then again go back here, and then go through one full cycle, and if you look at the magnitude of the voltage of the current here, if I'm looking at the current magnitude, if I have a maximum value as Im, it is essentially its projection on the y-axis is Im sine theta is this I, instantaneous value. So as we move this point, progress this point from 0, current 0, to the end of the cycle, you can see that this vector is rotating in a counterclockwise direction, one full cycle. So essentially, a vector, if it's rotating here, we call this a phasor. Phasor is nothing but a vector rotating at the system frequency. And then we also monitor this. If we have a maximum value, we find out what is the effective or root mean square value of this current. Instead of that, essentially what it is if you take this current and pass it through a resistance, the heat dissipated is equivalent to as if it is a DC current going in the circuit. So when you try to do that, you calculate the effective current or the root mean square value of the current, which is I squared, and then the relationship between root mean square and then the maximum value is Im by the square root of 2. These are basics which are going in. And then also in 3-phase system, phase sequence or the order in which they reach the crest values we are taken. Generators are designated to generate voltage that reach crest values successively at equal intervals. So if it is a 3-phase system, they are first A phase reaches the peak, and B phase reaches the peak here, and then the C phase reaches the peak. So if you look at it like that, they are 120 degrees apart. So positive sequence is the order of the rotation of the generated voltage, the counterclockwise direction. We take this as a convention, and the phase nomenclature is ABC, 1, 2, 3, RST, or RYB. So we have various, depending on which country you are in, these can vary. They have different terminologies for this. And also, our assumption that it is rotating in the counterclockwise direction is just a convention that is universally adopted. This is not true in the United States. In some parts, in Western part of the world, we have Western utilities. Their positive direction is clockwise direction. They thought that they should have clockwise direction as the positive sequence. So their positive sequence is opposite of everyone else in the rest of the world. That is a negative sequence, and the rest of the world will be positive sequence. So it is not true that all of them follow this convention. It varies depending on which part of which utility has this practice. So three-phase system balanced, if the voltages and currents are balanced at every point in the system, same peak magnitude 120 degrees apart, this is positive sequence. For this to be true, network impedance should be balanced and generated voltage should be balanced. This is what we assume in the analysis. That is why I made the statement here. We assume that the system is balanced and the generation is balanced, but the network may not be balanced in the actual network. And we will talk about what is the impact of that later. And abnormal situations as unbalanced faults in this, for example, A to ground or B to ground or C to ground, or A to B, B to C or C to A, or AB to ground, BC to ground, or CA to ground. These are unbalanced faults, and we will talk about them too. And then VAB is VA minus VB, as I said, and the designation is, the higher voltage designation is the first letter. The second letter is either drop dot if it is ground or neutral, and then A to B is from voltage A to voltage B is VAB is VA minus VB. Now, when you look at a network representation, when I look at the three-phase system, if it is balanced, there is no need for me to represent all the three-phase networks individually. They can be represented as a single-phase network. And what I have to do is, whatever results I get in analysis, I can shift it by 120 or 240 degrees to get the C phase and the B phase, other two phase voltages and currents, right? And then we also know that phase-to-phase voltage is √3. And the power factor is, power is the product of the current through the branch and then the voltage drop across the branch. When you do that, instantaneous voltage and times instantaneous current, if you expand it, we get this as power is P times 1 minus cosine of 2 omega t plus Q times sine of 2 omega t, where P is VI cosine phi, Q is VI sine phi. These V and I are RMS values, voltage and current. Now, when you look at this equation here, the active power, what we call it as P, it goes from 0 to 2P. And then when I look at the sinusoidal sine term here, it goes from minus Q to plus Q. That means active power is the one which is we are utilizing it. It goes from 0 to 2P, and then it is running at twice the frequency. And the reactive power is in every cycle, it is 0. The average is 0. That means it is returned to the system or it is consumed from the system. It is just an exchange of power and it is not lost anywhere. These are all just basic concepts. You can read any electrical engineering book that will cover this. And then three-phase power is square root of 3 times phase-to-phase voltage times I. Phase-to-phase voltage is nothing but square root of 3 times individual phase-to-ground voltage. That is 3 times V phase-to-ground times I phase. Or we can write it as √3 V phase-to-phase times I phase. These are some simple terms. We don't have to go through this again. It's just recapitulate what you studied as and in your course as Electricity 001. Now let's look at per unit and percent value. Now, if I have an 115 kV system as a nominal system, if the voltage is at 100 kV, we can express it as a percentage or per unit with respect to the reference voltage of 115 kV. We can write this as 0.89 per unit. It is a unitless value. So we are expressing this 100 kV as 0.89 or 89%. So it is a unitless value. It is not a voltage or amps. And if it is ampere also, you can represent the rated current to the actual current to the rated current, and we can represent as in per unit. So in calculations in per unit is used. Percent also can be used in equations, but this 100 comes into picture. You have to be very careful when you use percentage. So per unit, in a per unit system, as we see here, we have to have a reference value, and that should be assigned. Let's look at the simple system here, and we will use this system throughout our the analysis and discussions for the next three modules also. You have a 800 MVA 23 kV, and then you have a generator step-up transformer, which is 23 kV to 230 kV. And then you have a 230 kV system, which transmits this 800 megawatts from mega MVA from this generator bus to the load centers here. And also there are some load centers here. And then at the distribution level, the voltages are stepped down to 13.8 or 34.5, and finally it is stepped down further to come into our houses or buildings at 120 volts or 240 volts. Our industrial system, we can go up higher also. So we have several system voltages levels. Impedances are connected at these voltage levels. Calculations becomes difficult. For example, if we convert this into current, this is about 20,000 amperes on the generator, rated current. Now, when you go up this transformer, the power is the same, right? So the current here becomes about 2,000, nearly 2,000 amperes here. Then it goes down here, and then this MVA is different. This is not a 800 MVA transformer here. It is about 50 MVA transformer here. Then the currents are much higher here also around that. So when you move from 23 kV generator system voltage all the way to the distribution level, the voltages and currents magnitudes keep on changing, and we have to be very much aware of this transformation. Similarly, if there is an impedance on the low side here, and if you want to reflect it to the high side here, we said that voltage is proportional to the turn square, and the current is inversely proportional to the turns, and voltage is proportional to the turns. So if you take the impedance, which is voltage divided by current, the impedance is reflected onto the 230 kV side, 123 kV side, will be a ratio of the voltage squared, that is 230 squared by 23. So if you have an 1 ohm here, if you have measured some 1 ohm here, then that will be equal to 100 ohms on the high side. And when you come here, again, it reduces by the square of the transformer turns ratio. So you are looking at various numbers at different values, and it becomes extremely difficult to keep track of this. That is why we went into per unit quantities, where we define a reference value called the base value. We need 2 numbers out of 4 what we can get: MVA, kV, impedance, or current. They are all related, right? MVA by square root of 3 times kV is the current, and then kV squared by MVA is the impedance, and then they are all interrelated. And we can use 2 of those, and with this, we can represent all the impedances, and that's as a unitless quantity, and that takes away this voltage transformation from low voltage to high voltage, and again to low voltage. So if normally base kV and base power are taken as a reference for a 3-phase system. Phase-to-phase voltage is taken as a reference, and 3-phase power is also taken as a reference. Base impedance is the value that produces 1 per unit voltage drop across when the 1 per unit current flows through the impedance. So essentially, how do you express this? I can express it as phase to ground voltage which is V base divided by square root of 3 divided by the I base current. That gives me the impedance. I is in amperes, and then kV is in kilovolts here, right? That is why I'm multiplying it by square root of 3. The original slides had a mistake, so I have fixed this here with a red mark. So if you have already printed out the copies, please do correct this. And then Z base is kV squared by MVA, MV's values. So when you look at this, let's look at what happens to our example here. Generator is 23 kV and 800 MVA. So the base current is 800,000 kVA divided by square root of 3 times 23 kV. So it comes to 20,082 amperes. The base impedance is kV squared by MVA, that is 0.66125 ohms. Generally, the base MVA of the system is chosen as 100 MVA. So because all these transformers, generators, and then other quantities may all have different ratings. Current rating for a transmission line, if you convert it to MVA, that can be very different MVA. So in order to get a uniformity of expressing everything as then on a common base values, we choose 100 MVA on not the individual equipment rating here. If you go to industrial systems, they try to use 40 MVA as a base also. So you can choose any value you want as long as you're comfortable with whatever you're using and you calculate. The industry has chosen 100 MVA here in this case, and then that is what we use. Now, on 100 MVA base current is 2510. How do you get this? This is multiply this by square root of 3 and divided by 10,000, converting to kVA, it is 100,000 kVA divided by square root of 3 times 23. When you do that, you get 2510 amperes. So the generator voltage is 1 per unit. What is that 1 per unit corresponding to? 23 kV, and it is 100 MVA base. So 800 MVA corresponds to 8 per unit. Okay. And then the current now is, since 20,832 amps, if you express it in base MVA, base current, 20,082 divided by 2510, which gives you 8 per unit. So now if you go to 230 kV base, the base current on 100 MVA is 251 amps. Generator current, when you try to look at it, is 2008 amps. So when the generator is generating 800 MVA, the current on the 230 kV system is also 8 per unit on 100 MVA base, but at a different voltage base. So 8 per unit current is the power which is generated by the generator, and the same 8 per unit goes on to the 230 kV system. So what it tells you is the per unit values remain unchanged over voltage levels. This is extremely important for us when you try to represent a system as with equivalent impedances, and they are all expressed in the common level. Advantages of per unit representation: if you have characteristics of electrical apparatus that can be easily compared. Essentially what it is percentage impedance. If you look at it, it is the voltage drop across that is seen through the equipment when the rated current goes through that 1 per unit, or the current goes through that. So you can compare various equipment, especially transformers. You're trying to put two of them in parallel. One is, for example, if you take 100 MVA transformer, which has 10% impedance or 0.1 per unit impedance, and then you have a 50 MVA transformer, also 0.1 per unit impedance. So if you put two of them in parallel, and if you put 150 MVA load on that, then they share loads according to their MVA ratings. So for 50 MVA gets 50 MVA load, and 100 MVA gets 100 MVA load. This, as you go through, you will, if you go through and then look at these examples, then you might get a better picture of these. And most of the times, per unit values are close to each other for a rating of a transformer or generator. This is important because sometimes we may not have the values that we need to calculate the fault current and voltages at the relay locations. So if you have a similar transformer, then industry also that they try to let you know that these transformer impedances are very close for that rating, voltage rating and MVA rating. We can use, if the data is not available, typical values can be used for our calculations. Again, Z per unit is Z ohms divided by base impedance, which is kV squared by MVA. If you rewrite this, Z ohms is base MVA divided by kV squared. And then percentage Z is per unit times 100. This is all repetition of what I have been telling you. And then Z ohms is Z per unit times kV squared by base MVA. And then old, if you want to convert from 1 MVA to new second MVA. For example, if generator is 800 MVA and then the transformer is 965 MVA or so, you want to keep the same common base, you can convert the transformer impedance generator base at 800 MVA by taking the transformer per unit impedance, multiplying it by 800 divided by 960. That is how you can convert it. And the second also, the voltages may not be same. We say 23 kV and the transformer might be rated for 23.5 kV or 24 kV. So these two voltages are different. So you can take the transformer impedance and then convert it into 23 kV base to use it in the calculations. Essentially, we are using the same voltage at in that area, 23 kV or 24 kV are converted to 23 kV. And then, 230 kV can be 242. These are all converted in 230 kV base on that. And then these are the formula which are used here. Three-phase system, if I look at it, now if it is a delta connected, you can go through the calculations. It comes out to be phase-to-phase times I line, whether it is delta or Y, it works out to be the same number. Okay, I hope you are still with me. Essentially, what we did was we looked at the system, we looked at the impedances provided, and then we tried to convert everything to a common base. Especially we used MVA base or power base, power as one of the quantities and voltage as other quantity. So what we do in any system calculation is we convert all of them to their rated voltage and to a specified base voltage and base current, and we convert all the impedances that is required and calculate that at those values. Then once we have the network connected like that, then we go back to our old network theorems. Ohm's law is voltage equals I times Z, and Kirchhoff's current law is sum of all currents at any junction must be equal to 0. And then we also have a mesh law, loop law, where sum of all the voltages within a loop must be equal to 0. That means all the generated voltages must be equal to the voltage drop across the load inside a loop. Then we also use superposition theorem. Suppose if we have many sources and we are not very sure how they interact, we make use of the superposition theorem by just allowing all other sources shorted, voltage sources shorted, or if they're current sources, we open circuit them. And then we just take the effect of one and then we keep on adding. This is true only if all the impedances are linear. This is the key point. They have to use, the linearity must be true. Then we can use superposition principle. And Thevenin's or Norton's theorem we use if you have, if you want to look at the impedance from the point at which the fault occurred, you have to look back and you can represent this as an equivalent voltage source in the Thevenin or equivalent current source in Norton's, and then with a series impedance in the Thevenin by shorting all the sources, or a parallel impedance for the current source with all the other current sources open sourced. So these are basic theorems, and you have gone through this in your circuit theory class. I just wanted to bring it up to your attention here, that is all. So another transformation we use in networks is, because they are all interconnected, we have to convert sometimes delta into Y so that we can add and then parallel some of the impedances. So these are delta to Y, we use ZA is ZAB times ZAC divided by sum of all the impedances of the delta. And similarly, Y to delta ZAB is nothing but ZA plus ZB plus ZA ZB divided by ZC. So this is also used if there are equal impedances in 3 branches. ZAB is 3 times ZA, or ZA equals ZAB by square root by 3. Note if there are per unit values of these will be same if they are on the same base voltage and base MVA. So this is another one method we use. We use Mesh's law, Kirchhoff's current law, and delta Y transformation in the circuits. But now you have to assume that all you should have already realized that all these theorems and all our mathematical analyzing tools were all valid for single phase system. Now, if you look at our system, it is a 3-phase system, right? And 3-phase system, if it is an ABC to ground or ABC fault, then it is a symmetrical fault. Then we can represent that as a single phase circuit and then phase shift the calculated numbers to other phases. And then we can reduce this using these network transformations, what we were used to before. But in a 3-phase system, all the faults are not symmetrical. For example, you have a single line to ground, A to ground, B to ground, and C to ground. Double line to ground, A to B to ground, or B to C to ground, or C to A to ground. And then you have line-to-line faults not involving ground, A to B, B to C, C to A. These are unbalanced conditions, and then there is no easy way for us to convert these and then calculate the required voltages and currents at various points for a fault at a location. And so our conventional systems of delta Y transformations or current law, voltages law cannot be easily applied and interpreted to detect each individual phase voltage and currents. So in fault calculations, we want to represent as a single phase, and it is difficult to solve for these, as I mentioned. That is where the symmetrical components came into picture. You take a system of unbalanced voltages and currents, and then you represent it as a set of balanced quantities. And this allows a representation of the system with a single phase. So 1918 was the year when Fortescue, when he published a paper. It's about 50-page paper if you go back and look at it, or much higher it looks like. It's almost a book that was published as a paper which said method of symmetrical coordinates applied to solution of polyphase networks. The concept here is if you have a system of n vectors or quantities, they can be resolved into n different symmetrical groups. That n symmetrical groups, out of which one of which will consist of n equal vectors, and the remaining n minus 1 consists of n equi-spaced vectors. So this is what he said, but the n has to be prime number. So in our case, we have a 3-phase, 3 is a prime number. So they can be split as into 3 sets of vectors. One of them are 3 vectors which are equi-spaced. They are in parallel with each other. And the other 2 are set of 3 vectors which are equally spaced in 360 degrees. That means they're 120 degrees apart. So we can represent a 3-phase system as set of 3 balanced networks, balanced systems. Voltage can be written as A, B, and C. So when you look at it, they are rotating in the counterclockwise direction. So A, V, A, and then the phase rotation is A, B, and C. And then the second one, if you look at it, the phase rotation is A, C, and B. So it is opposite to the primary one, or we can say that these set of 3 vectors are rotating in clockwise direction if you want to maintain A, B, and C. This is counterclockwise, this is clockwise, and these are 3 sets of phasors which are rotating at VA0, VB0, and VC0. Again, the phasor is nothing but a vector rotating at system frequency. So all these are rotating, and then because the current magnitudes, voltage magnitudes are changing, but if relative to each other, they are almost stationary. The whole set of 3 are rotating at 60 hertz or whatever frequency that is coming in. So when you look at it, VA1 is the voltage of the A phase of the positive sequence. What is VB1? We make use of the mathematical operator tool, that is A, and then it is 120 and 240, A squared VA1, and VC1 is AVA1. Similarly, VA2 is here, if you take the A phase as the reference, and VB2 is A times VA1, and then VC2 is A squared times VA2. In the case of positive sequence, the B phase was A squared VA, and in the negative sequence, VB is AVB, AVA. And in the case of zero sequence, there are three vectors which are rotating, then that is VA0, VB0, VC0. So positive sequence of vectors are vectors of equal magnitude and are spaced 120 degrees apart. The rotation and time is the same as that of generated voltage ABC. The negative sequence voltage is similar to positive except that rotation is ACB. And the zero sequence are three vectors. They are not separated in time, but they are rotating in unison at the same speed. If you look at phase quantities, we can represent the phase quantities as sum of the three. VA is VA1 plus VA2 plus VA0. VB is VB1 plus VB2 plus VB0. Now you represented this as, in terms of A phase only, it becomes A squared VA1 plus AVA2 plus VA0. VC is VC1 plus VC2 plus VC0, which can be represented as AVA1 plus A squared VA2 plus VA0. Again, you spend some time and look at it. I'm just going through this so that we can go to the actual protection by tomorrow. And then we will go through this in the end and how we make use of these to calculate the fault current and voltage. As I mentioned in the beginning of the lecture, the intent here is not for you to sit down and calculate the fault current and voltages for various points by in hand. But nowadays you have computer programs available, and you have to know how you are representing or modeling these generators, how you are representing or modeling transformers, and also other equipment that we see in the system. That is the intent of this. So sequence quantities, if you add these numbers, VA, BB, VC, then if you add all of them, then you get 1 plus A squared plus A, that is equal to 0. 1 plus A squared is 0. And then so positive and negative sequence goes off, and you get 3 times VA0 is sum of these three. If you add 3 voltages, we get EA0. And multiplying 1, 2, 3 equations in the previous the slide with A1A and A squared, we get positive sequence 3VA1 is 1 plus EVA plus AVB plus A squared VC. Similarly, the negative sequence is VA plus A squared VB plus AVC. Now, just digress from here. This is not the only way an unbalanced three-phase network can be split into 3 sets of balanced networks. There is another method called alpha, beta, and zero, Clark's components, after the great Edith Clark, who wrote an excellent books on this symmetrical components. She was an engineer at GE and later on became a professor at Texas, University of Texas. And her contribution is enormous to this industry. Now, that is also available. Alpha, beta, and zero components were used extensively in static relay designs, because there was no need for us to shift by A or A squared operators in static relays. You just have to add and subtract numbers. So you can take actual values of voltages or currents and add or subtract by different scaling factors, and you were able to get alpha, beta, and zero component. Zero component was same as our zero component here. We don't look on it because most of them may not be using it, so we just stick to symmetrical components. So sequence quantities is V0 is 1/3 of VA plus VB plus VC. V1 is 1/3 of VA plus AVB plus A square VC. V2 is 1/3 of VA plus A square VB plus AVC. And you can also see that VA is sum of these three vectors. It can be represented graphically also. Or you can go into a matrix form, and VA0, VA1, VA2 can be written as 1/3 of a matrix 1, 1, 1, 1 A square, 1 A square A, VA, VB, and VC. Similarly, the current also can be expressed. The relationship between zero sequence numbers and phase relationship are given here with the same matrix conversion. So the reference for this are chapters 3 and 4 in GE's protection automation book, or network protection and automation guide of the older version. If you have any one of those, nothing has changed other than the title, and very few chapters have been added in this. That was done already by NPAG, by Alstom. Okay, we will take a 5 minutes break. I'll get into the round 2, and then we will finish it and then take a lunch break. Okay, we will start with this last one before lunch so that we can get refreshed. I'll give a longer break so we can meet at 1:35, and we will not cover bus protection today. We will do that tomorrow so that we can leave early, but you can take a longer break from noon to 1:30 or whenever we finish to 1:30, and then we can look at the last mathematical tool where whatever we have learned in these 3 modules, we will use them and then try to solve and then get fault currents at the relay location. We did per unit and percent quantities, and we also looked at how we can cover voltages, actual voltages and currents in amps to per unit basis. Okay, these are just a review of whatever we have done so far. And then we introduced symmetrical components. 3-phase voltages and currents represent 3 sets of 3 by a set of 3 sets of balanced vectors. By a set of 3 sets of balanced vectors, that is all it is. And the representation allows system to be represented as single phase system to solve for system voltages and currents under fault conditions. Okay. Now we also went through this. The B phase is A square VA1 of the A phase, and then C phase is A square. So when we look at this, we can always remove this A and then we can write it as V1, A square V1, and AVA1, V1, and then V2, AV2, and A square V2. And VA0 is V0, 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 because ABC doesn't mean anything here. So we can always express it as with respect to one phase, that is A phase, and we can take off the A here. And positive and negative sequence, they are equally spaced. Positive and negative are same set of 3 balanced vectors, but one is rotating in the opposite direction. That is a negative sequence clockwise, or if you maintain ABC vector here is in counterclockwise, ABC negative sequence is clockwise, or if you want to maintain the same counterclockwise, we can write the negative sequence as ACB as a sequence of rotation. And 0 sequence 3 vectors are not separated in time. Again, we went through these equations and then calculated how to get the values of 0 sequence from then the positive sequence and negative sequence from the phase voltages. What we measure are just the phase voltages, right? And we are converting that into sequence. These are the equations which we use to do that. And graphical method, and then we covered everything here. Now let us look at a generator. Now we will start looking at the impedances as in terms of sequences for different equipment in a system. Now if the generator generates only positive sequence voltage, so then I can represent that as EA, EB, and EC. These are the positive sequence voltages. I have some impedance up to the fault point. This could be the generator impedance if it is a terminal. Then the voltage at the terminal is EA minus IA1 Z1. That is a positive sequence impedance, right? And negative sequence, there is no negative sequence generation. So the voltage here will be minus IA2 Z2 and minus IA0 Z0. Just make sure this is the voltage drop across the impedance. The positive sequence, when you have a voltage drop across this, the voltage at the terminal will be generated voltage minus the voltage drop across this impedance. But if you look at negative and 0 sequence, there is no generated voltage, which is 0. So that is why VA2 becomes minus IA2 Z2 and VA0 becomes minus IA0 Z0. In short circuits, if you look at it, I have 3 phase, line to line, double line to ground, and line to ground. These are the 4. And now we will see how to look at this. Our definition is determine the voltages and currents at various points in a 3-phase system when a fault occurs at a specified location. I have a relay connected at, for example, monitoring a transmission line at station A. And the fault occurred somewhere close to station C in a network. And there, where the voltages and currents are measured, and I have to calculate what would I see as voltages and currents at the relay point at the station A, right? That again, the fault occurred at somewhere very close to station C in a network, but my relays are monitoring the voltage and current at station A, which is a lot further away with the network connections here. Then I have to determine the voltage and current. That is what our problem is. So now the solution to determine the unknown quantities at various locations. And we essentially various locations I'm telling, but most of the times we are looking at the relay to understand what my settings would be, and then how I can set my relay to protect only the faulted section. So unknowns are VA, VB, VC, and IA, IB, IC at the relay location. The solution process is to replace phase currents and voltage at the point of asymmetry. That is where the fault occurred, with sequence components. That is what we will do. So now let us look at where the fault occurred. Suppose if it is an A to ground fault, what happened to the A phase voltage at the fault location? That will be equal to 0. And then the B and C phase currents, let us assume that there is no load fault prior to that, or the load current is very much less when compared to the fault current value. And then we look at it as VB for A to ground fault, VA is 0, and then IB equals 0, and IC equals 0. And IA is not 0, IA is the short circuit current. Similarly, for a B to C fault, at the location, two wires are shorted together, two phases. So VB will be equal to VC, and then A phase current is 0. So A to B to C fault is VA, VB, VC will be equal to 0. And BC to ground fault is VB equals VC equals 0, and IA equals 0. The difference between BC fault and BC to ground fault, voltages are equal, but they go to 0 if it is shorted to ground. So a single line to ground fault, let us look at it. There are no fault currents in B and C. So now we will try to convert all these measurements, actual voltages at the fault, into sequence numbers. And then IA0, IB0, and IC, IA1 and IA2. If you look at it, B phase and C phase currents are 0. Essentially, the currents of sequence currents IA0, IA1, IA2 will be IA by 0, IA by 0, IA by 3, and IA by 3, and IA by 3. They are 1/3 of the total fault current that is flowing on the A phase. So all three currents are equal. And they are 1/3 of IA fault current. And VA equals VA1 plus VA2 plus VB2, and that is equal to 0, right? And then I can write this as VA1 equals what is A1 is generated voltage minus IA1 Z1. So if a fault occurred at that fault point, whatever that is behind this is the total impedance up to the fault point from the generated voltage. So the current is going through that, and then the voltage VA1 will be to E minus IA1 Z1. Similarly, VA2 equals minus IA2 Z2, and VA0 is minus IA0 Z0. But IA1, IA2, IA0 are equal for a single line to ground fault. So I can represent them as a negative sequence voltage is minus IA1 Z2, and zero sequence voltage is minus IA1 Z0. So now the voltage VA can be written as E minus IA1 Z1 minus IA2 Z2 minus IA1, as all of them are IA1 Z0, or IA1 can be written VA0, right? So IA1 can be written as E divided by sum of positive sequence, negative sequence, and zero sequence impedances. So now I know zero sequence current, I know the positive sequence current, I know the negative sequence current, because all these sequence currents are equal for a single line to ground fault. So I can write this as IA0, BA0 here, and then IA1, IA2, and IA0 are in phase. And then IB current is A squared IA1 plus AIA2 plus IA0. So if you do that, they all come like a delta. Here, they add up to 0. Yeah, as I mentioned earlier, there is no need for us to keep A, B, and C here because they are equal currents, but they are phase shifted by 120 or 240 degrees. We can write this as IA equals I1 plus I2 plus I0, and IB is A squared I1 plus AI2 plus I0, and VA is V1 plus V2 plus V0, and VB is A squared V1 plus V2 plus V0. I'm taking you through a lot of mathematical derivations, so please bear with me. It is almost lunchtime, and then also it is not a wonderful experience for you to sit and listen unless you go through each of these equations. So please go through this at your leisurely and then try to get a concept of this. So now I have a positive sequence impedance network, which has got a generated voltage and then an impedance up to the fault point, right? And then you have a negative sequence impedance network and zero sequence impedance network. Now, what happened in the A phase to ground fault? I1 was equal to I2, that is also equal to I3. So if I have three networks where I have same currents flowing through all of them, how should my connections be? They should be connected in series. So this is how these are solved. So the current that is going through the sequence current will be equal to total pre-fault voltage divided by sum of all the impedances up to the fault point. We are looking at the fault point, how these are connected. That is how we get this. So fault analysis, what we do is we identify the type of the fault and determine the fault current and voltage relationship at the fault location and derive sequence currents and voltages. Where are they at that fault location, and determine how the sequence network gets connected to solve sequence currents and determine the sequence voltages and then determine voltages and currents. So the last two, you keep on going back in the sequence network in using your delta Y transformations and all, and go to the point where the relay is located and, and then calculate the sequence currents and voltages. You should know that here the sequence currents and voltage, positive sequence will not affect the negative sequence or zero sequence. And similarly, the other two sequence networks will not affect the positive sequence network. This is possible only if you have a symmetrical network and also symmetrical fault voltages. May not be possible, so there is some influence, but for most of the analysis purposes here, we try to assume that everything is symmetrical in the world. And then if you look at A phase to ground fault, what happens to the B phase and C phase fault voltages? So if you derive these equations, VB is A square V1 plus AV2 plus V0, right? V1, V2, V0 or components of the A phase. Now, if you try to solve this equation, then finally we get VB is A square E1, E, that is the voltage shifted by 240 degrees, minus Z0 minus Z1 divided by Z0 plus 20 times E. That is just the voltage on the A phase that is getting shifted by, it gets added on to the pre-fault voltage, that is A square E. So when you look at that, then similarly we can write that VC is same as this. So this is Z0 by Z1 minus 1, Z0 by Z1 plus 2 times E. This is also same. So when you look at this, under normal system, Z0 by Z1 is not scalar, but typically Z0 is 3 to 4 times Z1. If you take Z0 by Z1 as 3, you find out that B phase voltage increases from 1 per unit to 1.25 per unit, and the angle changes from minus 120, that is 240 degrees, to minus 136. So when you try to see that, for this is the pre-fault voltage, as soon as A to ground fault voltage, the voltages shift at the fault point, the voltages rise to, on unfaulted phases, rise to 125, 1.25. So depending on the ratio of Z0 by Z1, the voltage on the unfaulted phases increase. So if Z0 by Z1 is infinite, then this will be equal to phase voltage, 1.73 E. square root of 3 times E, that is phase-to-phase voltage. And then if Z0 by Z1 equals 1, then you can see that it will be same as the pre-fault voltage. It doesn't change much. So this Z0 by Z1 ratio is called the ratio for effective groundedness. And the system, we always monitor this, and we say the system is effectively grounded if X0 by X1 is 3, and then R0 by R1 is 1. So this ratio of 3 of X0 by X1, and if you look at it, that essentially limits the voltage rise on unfaulted phases to about 25%. So this is a requirement in an effectively grounded system. And most of the systems from 69 kV and above are effectively grounded system in the United States. We might have some Peterson coils on 69 kV. I'm not sure where they are, but definitely 115 kV and above, they're all effectively grounded systems. Now let us look at the phase-to-phase fault. Here we have two voltages are equal, VB equals VC, and IA is equal 0, IB equals minus IC, because the current comes on one line and goes back on the other line, right? So let's see whether I have a pen. I have it here. Where did I keep my back? No, it's here. Oh, I kept it here. When you look at this, this is a line coming in, and there was a fault here, and this is a line going out. This is IB, and this is IC. So IB equals minus IC for a phase-to-phase fault. And we can write this, and if you go through the equations, it works out that you have to connect the the positive and negative sequence network like this. So the current, that is I1, will be E divided by Z1 plus Z2, and then B phase current is A squared Z1, A squared I1 plus AI2. So if you do that, now you can calculate the phase currents. Similarly, if it is a B phase to ground fault, a double phase to ground, phase to ground fault, the voltage becomes 0. So the current I1 is split between Z0 and Z1. So essentially it is E divided by Z1 plus parallel combination of Z2 and Z0. That will give you the current. So this is how we convert the voltage, phase voltages and phase currents for an unbalanced fault at the fault location to sequence components. Then once we have sequence components, this is for the three-phase fault, it's same as sequence components. Then we go back and then look at how we represent as single-phase systems, and then calculate the currents of sequence currents at the required location for the voltage and current. So this is a very quick review of sequence components. Sometimes this is offered as a course by itself on methods of sequence components and learning. But here we have tried to cover it in about an hour. And the GE PAAG book, chapters 3, 4, 5, they take you through that. So hopefully you're still with me. And then, as I mentioned, the first half of the day will be very interesting. And second half of the day, you might get overloaded a little bit, but watch out for the next 2 days also. So we will cover the next 2 sections of fault analysis in the afternoon after lunch. Thank you. There is a question here. How do I do this? Escape?
Yeah, you can stop sharing.
Okay. Yeah, there is a question here. How does the load current affect the fault current analysis? It is assumed that only fault currents are flowing in the network, but in practice, before and after the fault, load current is supplied by the system. So a load, if it is a symmetrical load balanced, it is essentially the positive sequence current. It gets affected. Most of the cases, we assume that fault current is much higher than the load current. So it may be, for the analysis to understanding to understand this, we do this. But if you look at the load current, you have to add that as a positive current. And in the case of negative sequence, it gets subtracted also. So the details are covered if you look at a relay called KD relay, polyphase distance relay. They have the impact of load current on that is discussed, and there is a paper published by Westinghouse. But to answer your question, the load current is considered as a positive sequence current. It gets added to the positive sequence. If there are no other questions, let's take a break, and then we will meet you. What time is it? It's 11:53. So probably 1:15 or 1:30. Let's make it as 1:30. You can go through the previous slides and then make sure that have imparted some portion of it so that you can understand. We will be back at 1:30. Stopped.
Yeah.
We lost this.
Yeah.
That's okay.
You can go to share.
Yeah, sure. So this was just a run around by what we did here was in this section, we looked at the impedances of each generator, transformer, and then the network, and then we connected it, and then went back and calculated zero sequence and positive sequence current. Now, where did we calculate the sequence currents? If you look at it, we were looking at the fault point, that is bus 3. Now, if you have a relay at bus 1, where is that relay? That relay is sitting here, right? So you have to go back and take these impedances, and then you have to go backwards and calculate the current that is coming in here from this using inverse conditions, and then find out how much of positive sequence current is coming from these what is the contribution of each sequence current for a fault at bus 3 from these lines, and then you can reconstruct the phase current and phase voltage on that. It is a tedious task, so it is a lot easier nowadays that we don't go through this. We use power programs to take care of network solutions. So that pretty much comes to the end of what I was thinking. I would not start the bus protection here because I know that it is already super saturated day with a lot of mathematical analysis, and then what was covered in 2 months is covered in about 4 or 5 hours here. So just please go back and look at it, and then if there are any homework problems which you want to attempt, you can do that. And if you have any questions on that, we can look through that on the last day again. So just to summarize what we did today, we initially looked at the fundamentals of protection in the morning, where we looked at requirement of redundancy. That is, if a primary protection fails, we need to have another protection scheme that operates. For those practicing engineers, you know, the NERC does not allow single contingency failures not to clear the fault. So it is important for us to focus on it and make sure that you put enough protection schemes so that if one protection fails, there is something else to back it up. So we also looked at breaker failure protection, that is the interrupting device protection, and how we provide detection of that, and then how do we take care of clearing the faults or opening out all the sources to the fault. And that is also equally important. So first session, we looked at those two, and then we started looking at instrument transformers, where we looked at the CT and looked at the potential transformer too. And CT, as I mentioned, the fault currents, depending on the fault inception, has a lot of DC currents. Voltage waveforms do not have that much of DC offsets because the line impedance and system impedance angles are very close to each other. And then the sine of that very low angle reduces the DC transients quite a lot. So we generally don't talk about transients in voltages, because DC offsets in voltages, but we always talk about DC offsets in currents. There are different methods that is used in microprocessor-based relays. They use mimic filters for current to kind of take off the DC, and then for voltages, they have differential circuits that takes away when they do the sampling, they do X1 minus X2 plus X3 minus X4. They take away the DC offsets, transients, if it is there in the voltage also. Then we looked at three-phase system. We introduced the concept of the vector, and then also a phasor. Phasor is nothing but a vector which is rotating at 60 hertz. And we assumed that the frequency does not change in all these discussions so far. In actual system, when a fault occurs, the generators speed up and they change the frequency. It does have some effect, but in order to understand these concepts, we are keeping the frequency same. Then we went through and looked at faults in a single phase system and what methods are used. We used Kirchhoff's current law or mesh and loop equations. We said that total voltage within a loop must be equal to total voltage drop on all the elements within the loop, or sum of those must be equal to 0. And similarly, sum of all currents at the junction must be equal to 0. Then we also said that in a mesh network, we have to convert some deltas into Ys and Y to deltas for analysis, or simplifying, or for network reduction techniques, as they are called. We looked at those network reduction techniques also. Then we came to the three-phase power. Then we said if it is a balanced fault, three-phase fault, then we can represent that as a single-phase circuit, and then use all these network reduction techniques to calculate the voltage and current at a particular location for a fault anywhere in the system. Now, if it is an unbalanced fault, then these techniques do not work, and then it becomes very complicated for us to represent. That is where we introduce the concept of symmetrical components. Symmetrical components takes the three-phase the system and breaks down into three balanced systems, two of which are equally spaced equally spaced. That means if it is a three-phase system, there are three voltages, balanced voltages of which are 120 degrees apart. We call them positive and negative sequence voltages. And then we have three of them which are not electrically apart. These are rotating at 60 hertz. And these phasors, we call them zero sequence voltages or currents. So we took the unbalanced voltage and unbalanced current and split them into balanced voltages of two, which are spaced at 120 degrees apart, and one which are in parallel. They are not separated. And then we make use of them and converted an unbalanced system into a balanced system. Then we looked at the analysis of the fault. We said that at the fault point, we look at the boundary conditions. For A to ground fault, the voltage of the A phase goes to 0. For B to C fault, VB voltage will be equal to VC voltage. And for BC to ground fault, VB voltage and VC voltage will be equal and also will be equal to 0. We took these three and looked at how, if we have a positive sequence network or a negative sequence network or a zero sequence network, how they are all connected. As you saw here, whenever there is a ground fault, the zero sequence comes into picture. Whenever there is no ground involved, there is no zero sequence. That is it's an observation. If you have done that, I didn't mention it, but that is what that is what happens when you look at these, when you review this. Then we also looked at finding out if we don't. After that, we started looking at how do we create the network sequence networks. We looked at the generators impedances, transformer impedances, and transmission line impedances, and then we recreated this network, right? And then if we don't have the values for these devices, for transformers, transmission lines, or reactive elements, shunt reactors or shunt capacitors, we can go back and do the testing and calculate the sequence impedances. Only for the generator, we had to rely on the manufacturer. We get those numbers, and then we develop these networks. Then later on, we went back in the last segment, how to put together all these numbers, which we calculated before, and then calculate the currents for a fault on bus 3 of this network. So essentially, we went through understanding of the sequence networks, creation of the sequence networks, and connection of the sequence networks, and then calculation of the sequence currents, which are again translated back to the phase currents and voltage. So at this time, we will stop here, and then we will come back in the morning and cover bus protection, transformer protection, and transmission line protection. I think that will take care of most of the time tomorrow. And then the day after tomorrow, we will look at shunt reactor and shunt capacitor protection, and then also feeder protection on that. If you have any questions, please do share and then send a note at either IEEE.org at pratap.mysore@IEEE.org or at CUSP. These you can chat box. You can put these, and then we can answer them as when we restart tomorrow. So have a nice evening, and hopefully you got 10% of what I told. This is what Professor Bruce Wallenberg always told me. It is always good if students get, or if listeners get 10% of what you say. And hopefully I am able to convey, and then hope you got some understanding of what we have done so far today. Well, have a nice evening. We'll see you again tomorrow. Thank you.